Good evening, everyone. We are in the third week practice session of the course Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. And the third week is about MATLAB Model Development under Digital Control. So in this lecture, I will be discussing about I will be discussing about the analog control MATLAB model implementation, and then I will go into the digital control implementation in MATLAB as well. So let me share my screen. Let me know when you can see my screen. Hello, is my screen visible? Hello.
Yes, sir.
Yeah. Okay.
Yes, sir. It is.
Yes. So I am Tejagola, third year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. And today we have week 3 practice session, and it is about MATLAB custom model development under digital control. So let me give a summary of what we have discussed in week 2. So week 2, we have discussed about fixed and variable frequency digital control architectures, different sampling methods. So what is uniform sampling, where we will use uniform sampling, what is event-based sampling, where we'll be using event-based sampling, and what is interval 1 sampling, what is interval 2 sampling, and why we are considering TH delay, 1 second delay, all these aspects we have considered. So like a summary, we have discussed fixed frequency current mode control as well as variable frequency current mode control. So in fixed frequency, I have discussed peak current mode control and as well as valley current mode control. Average current mode control I have not discussed, but it is similar to peak and average, everything will remain same. So here we are using uniform sampling because this is fixed frequency. So you have to like remember this, because when we are doing MATLAB simulation, we'll be using uniform sampling in fixed frequency, and coming to variable frequency, we'll be doing event-based sampling. So how to implement all these things that we'll discuss. So in variable frequency, we have constant on time, and we have discussed why it needs a minimum of 10. So why it needs minimum of 10 and why constant of 10 needs minimum on time. I have discussed the necessity of the circuit. I'll be again discussing why we need it, and now I'll also be discussing how to implement in the MATLAB. And then we have discussed hysteresis, current mode control, peak, valley, as well as average, and how it will be working, all those things we have discussed. So today also we will be discussing all these architectures. So first I'll be discussing the analog implementation, analog MATLAB implementation, custom MATLAB model development under analog control, and then I'll be discussing about the digital implementation. So this analog implementation was discussed by Sir in the previous course, which is the control and tuning in switch mode power converter. So this has already been discussed by Sir, but I'll give you a free brief review. And so even if you have not gone through that course, so I'll do a revision kind of thing, so which will be helpful to you. And then in this course, Sir has discussed the digital implementation of the same architecture. So what are the building blocks of the digital control? Why we are using those digital blocks? How to implement them? What is the importance of those blocks? All things Sir has discussed, and I will also be discussing again in this today's session. So coming to week 3, so we'll be discussing about the MATLAB custom model development under digital control. So as we are doing digital control, we can implement the digital control in MATLAB as well. It needs some building blocks that we have to make. So we'll be discussing about that building blocks. So this session, I'll be discussing mainly MATLAB simulation. So I'll be like making the MATLAB live demonstration. So if you have any doubts, you can ask at any time. So as I have told, this first part was discussion in control and tuning in switch mode power converters. This is a previous course. So if you want a detailed explanation of all these things, you can go through the previous course, only the specific videos. You don't have to go through the entire videos. And also I'll be demonstrating these things in today's session. So if you have any doubts, you can ask. So in the analog control, I'll be considering these three. First, I'll be considering voltage mode control, and then I'll consider peak current mode control. So again, these two are fixed frequency. And this is analog. There is no question of sampling because it is analog. It is neither uniform. We don't need any sampling. So it is continuously driven. So that's why it is analog. And this is variable frequency. So first I'll show the MATLAB demonstration of this. And before moving into digital control, so we need to understand about the digital PID controller. So what is digital PID controller? How to implement in MATLAB? So what are the challenges and how do we face them and how do we solve it. And coming to the digital control, whatever that we have discussed in the analog control, the same things we'll also be discussing here, but in detail. So I'll discuss about voltage mode control, and in fixed frequency current mode control, I'll discuss mixed signal and fully digital. So we have discussed mixed signal as well as fully digital. So how to implement fully digital, because we are emulating the inductor current. So I'll discuss that, and constant on time as well as constant off time. So now this is a variable frequency, right? And these two are fixed frequency. Now, as we are moving into digital control, now the question will come whether it is uniform sampling or event-based sampling. So this is uniform sampling, and this is event-based sampling. So there are blocks that can be used for sampling. So how we are using for event and how we are using for uniform, I'll be discussing in the MATLAB. And then hysteresis. So this also comes under variable frequency, and for this also we'll be using event-based sampling. And then we'll solve few problems on MATLAB. So this will be at the end. So this is not the main thing. So understanding the implementation of the MATLAB is the main thing. So if you understand this, then you can easily solve the problems. And problem solving is actually based on the MATLAB implementation. So if you are confident about all the MATLAB simulation, then you'll be able to solve the problem. So let me start. So first I'll be discussing about the analog control. Again, this is in the previous course, not this course. So whatever I'm teaching you, I'm revising the concept that has been covered in the previous course. So no questions will be asked from analog control, but it is necessary for you to understand all the architectures and the implementation. So first we'll discuss about the MATLAB implementation in analog control. So as you know, in voltage mode control, so previously, if you remember, there is an ADC here. But now since it is analog, we don't need ADC. And previously everything was in FPGA. Now everything is in the circuit. So V0 is subtracted from V reference. It is going to V error. And GCS. How do we implement GCS in analog? We use op-amp based implementation. So we use op-amp if we are using PID controller or maybe type 3. So there are circuit for op-amp, and you have to make that circuit, and you have to choose the resistors and capacitors accordingly, and then you can implement the controller. And then there is a comparator. So for comparator, you use another IC for comparator. So we use a IC for comparator, and then that will go to flip-flop. So these are not in the FPGA. So as this is analog, so whatever we will be discussing in the first part, it is analog. So as it is analog, everything will be outside FPGA. So here there is no question of FPGA. And as you can see, it is a RAM. It is not a counter. So the counter is in digital, and a ramp is in analog. So they use some different circuit to generate this analog ramp, and then they compare it with the reference voltage coming from the PID controller, and then accordingly they will get the signals, and they send it to RS flip-flop, so that even if there is some noise here, it will not catch in the output. So this is about voltage mode control. So before going into current mode control, I will show the MATLAB demonstration of the same thing. So I guess you have gone through the code, so I will be somewhat explaining what is what in the code. So what we do is we do not just simply implement in the MATLAB Simulink model. We write code and we access the Simulink model through the code. So this is the main file, buck converter control file. And before we start, is the font visible to you, or shall I increase the font? Is the font okay?
Okay.
Okay. If anyone has any issue, you just tell me. I can increase the font, both this one as well as this one. So these are the folders that are available. I mean the files that are available in this folder. And this is the main converter control.m, which is the main code file. So it has buck parameter. So buck parameter is another file. We are calling that file. And what is there in buck parameter? All the LC values, T, tau D, R1, RD, all these values are available. So you don't have to mention it in the main file. So SAR has mentioned in the buck parameter, and they are not touched. So that's why we have
Sir, may we access these files?
You should ask the NPTEL people. I'm not sure whether these can be given to the students or not. I got this from the course instructor, but you can talk to the NPTEL team whether you can get these files or not. I'm not aware whether you'll be given these files.
Sir, from where we can get these files?
whatever that can be given to you, that the professor has already given NPTEL. So if they can give you the files, then NPTEL people should give you the files. So maybe you can mail the NPTEL people, the help desk, whether you can get these files or not.
Okay.
Since I'm actually a TA, so I don't have any authority over these files. These files I got it from the professor, and whatever you can get, that NPTEL people will be providing you. So you just contact. So this is the parameter file that we are accessing, and then switching frequency we are defining. V reference is nothing but output reference voltage, and then resistor we have set it to 1 ohm. So since V reference is 1, it is a buck converter. R is 1, so current is 1 ampere initially. And then they are setting the modulator gain. As this is simulation, there is no you can choose any modulator gain, but when it comes to the Verilog, you cannot choose any modulator gain. So keep this in mind that when you actually make the hardware, there is this restriction on the modulator gain. Why it will come, that I will tell you when we discuss in the Verilog coding of analog voltage mode control. I will discuss at that point. But now it is simulation, so you are free to choose any modulator gain, because accordingly the gain will change. But in the actual hardware, there will be limitation, and how we can get the modulator gain, everything that I will discuss there. And PID controller also, you have to keep in mind that whatever designs that we are making, that will not be, let us not discuss about the controller design in this week. Next week, SAR will be discussing. So what are the methods that we have to consider for designing everything, that SAR will be discussing. So in this session, you might have questions about how we are choosing KPK KD. So please hold on, we will discuss in next week. So this week, today we will be mainly concentrating on understanding the working of MATLAB and all the subblocks. And PID controller derivative, you cannot actually use pure derivative. So there is something called practical derivative, which will have tau d term in that. So for the tau d, we are considering very less T/5. And so these two will be the controller gain. So if you consider say PID controller, we have what Kp plus Ki by S plus KDS by 1 plus tau ds, right? So this tau d is because of the practical implementation. You cannot only implement KDS, because of which we are getting this tau d. So now if you multiply, you will get tau d S square plus S in the denominator, and in the numerator you will get Kp into tau d into S square plus Kp plus Ki into tau ds plus Ki plus KDS square. So if I write this again at the bottom, what is the S square coefficient? Kp into tau d and Kd, and S coefficient Ki into tau d, and normal S to the power 0 is Kp plus Ki by S square tau d S square plus S. So if you see the coefficients, Kp tau d plus Kd, Ki tau d, Kp plus Ki. So that is what SAR is writing here. So first one is Kd plus Kp into tau d, Kp into tau d. And then second term is Ki into tau d. Kp plus Ki into tau d. I think I have missed one Kp term. So sorry, this will be Kp into S. So this will be Kp into S. So there will not be Kp here. Here we'll get Kp. So the second term is Kp plus Ki into tau d. So this is the second term, Kp plus Ki into tau d, and the last term is Ki. And in the denominator we have tau d S square, tau d S square. So tau d, and the next coefficient is 1, and the last coefficient is 0, right? 0 into S to the power 0. So that's why we have put 0 here. Now GC is we can use a function, transfer function of numerator polynomial by denominator polynomial. Now this will give us GC. So in the MATLAB we have a code. So now this is given as GC, which we'll be using in the MATLAB model. And SAR has different options. So option 1 is voltage mode control. See, this is the voltage mode control. Where is voltage mode control? VMC. So this is VMC, and option 2 is peak current mode control. Peak current mode control. So SAR has made different symbols, and all of them can be accessed from here. So one sibling file SAR has named OP1, other one OP2, and this is constant on time. Sorry, constant off time. Peak means constant off time. Value means constant on time. So OP3, OP4. Now here you can enter the file name, and depending upon what you enter, the particular Simulink file will be run, and that accordingly results will come. And these are the transient parameters. So the overall simulation time SAR is considering 5 milliseconds, and the step time is the time at which the transient is happening. So that SAR has mentioned 2 milliseconds. So from 0 to 5 milliseconds and 2 milliseconds the transient will happen. And this is delta I naught, load transient, delta V input voltage transient, delta reference transient. And now buck converter simulation. This is another code. So now I'm going to buck converter simulation. In buck converter simulation, SAR is accessing the data. So this is just how to access the data from the Simulink file. So from the Simulink file, SAR is getting the data, and SAR is saving it in a parameter IL, and then VRAM, and then V0, and then VCOM. So now SAR is getting the data. So SAR has to plot the data. So if you go back to the main, we have plot buck. So plot buck. If we can go to plot buck. So in plotbuck, there are figure 1. So these are just the basic commands where we are giving Y label and X label and the different font size and font name that we are actually writing in the code. So every time we don't have to change. So in figure 1 has 2 subplots. One is IL and the other one is V0. So now I have discussed the working of the code. So let me move into the Simulink. So you are understanding, right? Like whatever I am discussing. If you have any doubt, you just ask me at the time. Don't wait till the end. Hello, am I audible? Hello.
Yes, sir. Yes.
Okay, okay. So in throughout the entire course, the block will be the same. So we have one power stage as well as one controller stage. So when we go into current mode control, this part will remain same. Only this part will change. So controller part, whatever SAR will be implementing the new controller, that will be inside this controller one. So this is power stage. So just to discuss, it needs one input voltage, and this is V in step. So we are discussing about input voltage step transient. So here SAR is giving the input voltage step transient. So if I double click it, I will get delta V in. So delta V in we have mentioned in the code. So delta V in is 0 means there is no input voltage step transient. And this is a DCM enable. And this is I naught step, and V naught by R is I naught, right? So this term is I naught, and on top of that we are adding I naught step. So if you want any transient, then accordingly it is a step function. So we are mentioning the step time, which is T step. So at this step, if you want delta I naught so to be 20, then that load transient will happen. So now this is the power stage. It is taking the inputs and it is giving input current, inductor current, capacitor voltage, output voltage. And this is a mux. And this is buck result. So to workspace means whatever data that we are collecting here, it is coming back to buck converter simulation. So it is coming back here. So you see T is equal to buck result dot time. So this is the buck result. From buck result, we are accessing time as well as we are accessing data. And then using different parameters, SAR is saving the data in different parameters. Now let me come back here. So if I go into the power stage, so there are sub blocks. SAR has already discussed in the previous course. I will just give a brief overview. So SAR is generating the switch node here. So VX is the switch node, and this is the DCM enable block. So if you want to enable DCM, there is something called DCM enable here. So this parameter. So there is this parameter DCM enable. So if you want DCM to be enabled, then you have to make it to be 1. Else if you don't want, you have to just make it 0. So now that we are using synchronous buck, so DCM is not enabled. So DCM I am putting 0. So accordingly QD will be 0. So from the switch node, I am going into the inductor dynamics. So SAR is subtracting from the switch node, the V naught SAR is subtracting, and then SAR has 1 by inductance here, and then using the integrator. And then there is also a DCR of the inductor, which is denoted by R. So these are the inductor dynamics. And coming to the capacitor dynamics. Capacitor dynamics, you know, IL minus I naught is IC, right? So IC is going into 1 by C, and it has an integrator which gives capacitor voltage. And capacitor has something called ESR, equivalent series resistance, because of which the voltage across capacitor and the output voltage will not be same. Output voltage will be somewhat higher because there is a drop across this resistor. So SAR is adding this plus this, and sir is getting V naught. So this is IC. So IC into RC plus VC is giving V naught. So that is what is given here. So this is the power stage, and it will be constant throughout this course, and all the simulations will be changing only this controller block. So now let me go into the controller block. So controller block, what do we have? So here we have V reference minus V naught. So this is V error, right? So whatever that we are discussing here, so we are getting V error, and it is going to GC of S. And GC of S, whatever coefficients we have already defined in our code, and that will directly come from here. So it has a numerator polynomial, numerator con, and denominator con, which will be coming from the code. So this is our PID controller or type 3, whatever you want, you will be simulating. Output of his control voltage. And this is compared with what? A RAM. So it is compared with the RAM. And Sir has also discussed something called input voltage feed forward. So in the case of buck converter, it has poor line regulation. So if you want to make it better, they use something called input voltage feed forward. So even if you do not use, it is okay. But if you use line regulation will be better. So this is the RAM that is being compared with the comparator. So as you can see, here is the RAM, and this is the control voltage they are comparing, and it will go to reset. And it will go to reset, and from the set pulse, we are so FSW is a fixed frequency. So time period is set by T, and pulse width is setting 1%. So because it needs only rising it, so that should be enough to set. So now this is going to the gate pulse, and gate pulse is coming back to the power stage. So now if I simulate it, I just have to mention. So I need OP1. So I'm just simulating OP1. So let me run. Do you have any doubts in the voltage mode control implementation?
Yes, sir.
Yes.
What is the converter block in convert block?
Convert. Okay. So whatever FSW that it will be giving,
Okay.
and whatever set. So set needs Boolean function, and FSW is a double function. So you cannot give a double to Boolean. So you need a data conversion which converts the data from double to Boolean. So this block needs a Boolean input. So the data is not compatible. So it will not do anything. Everything will remain same. Now the MATLAB will simulator will detect this signal as Boolean. If you convert this directly here, it will throw an error saying that the data type is not matching. So you just have to use a data conversion.
So data conversion block is available in MATLAB, right?
Yes, yes. I think you just have to mention data type conversion. So that block you can use, and in this you can actually you can use output data type, input data type. You can change from any data type to other data type. So it is like flexible. You can change it from any data type. So this is actually very simple thing. Everything remains same in digital, except we have to digitize a few things that we'll discuss. So this is the simulation, and we have given a load step transient. So from 1 ampere to how much 20 amperes we have given. So this is like very nicely controlled converter, because the transient response is like very fast. So I think Sir has used last signal to. Let us not discuss about the controller. Let us assume that we have put some gains and we are checking the response. So like it is going from 1 ampere to 2 ampere, and depending upon the gains, as you know, the transient response will affect. And this is the output voltage. So it is like very fast, and it is trying to recover. So if you have it, and it, as you can see, it is taking much longer time, and it is reaching. But I think it is within the 2% error. So I think it is reaching very quite fast. So if you are clear about this voltage mode control, we can go into the current mode. If you have any doubts, you can ask me at this point of time. Else we can move to current mode. Yes.
Sir, actually, we are exporting that buck converter output back to the workspace.
Yes, yes. So like what we want to do is, either you can connect the scope here. So there is scope. So you can connect the scope here, and you can view it here. But we don't want to view it here. We want to change it from here. So we want the data to be coming into the code. So for that, there is something called to workspace. So to workspace block is there. So you can use this block, and you have to give the variable name. So Sir has given a variable name of buck result, And that buck result, how SAR is accessing here, converter simulation. So that buck result dot time. So buck result has two results. One is buck result dot time and another is buck result dot data. So SAR is accessing that. So maybe I can show here workspace. We have buck result. So in buck result, we have time series as well as 4 data series. So time series I am accessing in T and the data series I am accessing in X. And as you can see, X has 4 data depending upon how you have given the data. See, depending upon that same like order, the first data is inductor current, then ramp, and then output voltage, and then control voltage. So now IL means inductor current, V ramp means ramp voltage, V naught means output voltage, V con means control voltage. So now then SAR is plotting accordingly. See, SAR is plotting IL, here SAR is plotting V naught. If you want something else, you can plot that as well. So now they are actually in the in this variable, so you can access it easily. So if I want to plot IL and V naught in the same plot, I can do. If I want in subplots, that is what SAR is doing, I can do. So you will have this flexibility. That's why SAR is taking this data into the code. But you are free to you can connect a scope and you can check it here as well. It is up to your convenience.
Sir, does it comes under closed control?
Yes, this is closed loop control because you are using a controller and it is giving the gate pulse.
Sir, here we are using the feed forward only, right?
Only the input voltage feed forward that we are using, but other thing is feedback. So our output voltage feedback we are using, and input voltage feed forward SAR is using to improve the line regulation.
Okay, sir. Sir, I have a doubt in interval 2 sampling with 1 cycle delay.
Okay,
Please explain that when the
yes,
time permits.
yes. So it will be coming in variable frequency or fixed frequency current mode control. So at that point, I'll be discussing the interval 1 sampling, 2 sampling. You please point out at that time.
Okay, sir. Thank you.
Okay. So now that we have completed this voltage mode control, let us move on to the peak current mode control. So in current mode control, everything remains same except this block. So instead of comparing it with the ramp, we are comparing it with the inductor current. So now here it becomes PI controller instead of PID controller because it is a current mode control. It will be reduced order system. So PI controller should be error. So we are getting V error and then it is going to be I control and then it is giving I reference, which is then compared with the inductor voltage, and this is giving me reset. So everything remains same except this block, and P we will not use PID, we will use PI controller. So this is for voltage mode control, and this is for current mode control. Just a heads up.
Sir, what happens if PID is used in current mode control?
So that like that will come from the small signal model. We don't actually need PID. We just need PI. So that we'll discuss in the controller design thing. Why only PI is sufficient, why not PID? So it actually comes from the transfer function GVC of S. So GVD of S. So that loop transfer function we will consider, and from the loop transfer function we'll decide whether we need PI or PID. So we want to achieve a bandwidth of FSW by 10 as well as phase margin to be 60 degrees, right? So for this, what is the requirement of the controller? Whether we need PI or PID. In voltage mode control, we need PID. Just a heads up, there is less than a minute and the meeting will be stopped. I request you to again join in the same meeting and we'll continue the discussion. Hello.
Yes.
Okay. So for that reason, we only PI is sufficient to do this. So if we only PI is sufficient, why to go for PID? So it is why will we implement a complex thing? So that's why we only PI is sufficient. And derivative action, we actually sometimes don't use dielectric derivative. We use load current feed forward, which will also act as a derivative, and that SAR will be discussing in the upcoming. Sir, it is not allowing me to unmute. Okay. Let me check if I can do anything from my side. Stop. This is hello Banerjee, are you able to unmute yourself now? Hello. No, sir. Actually, everyone. Hello. Is other are others available? Like are others
Yes, sir.
can unmute. Okay. Then I think Banerjee, there is some issue with your mic itself. You just check if your mic is connected properly. Or you can ask the questions in chats and then I can answer. And check your audio connection whether your mic is connected properly or not. So that is all about current mode control. So let us move on to the MATLAB simulation. So again, we are going to the current folder. So in OP2, current mode control is there. So I just have to change this to OP2. So before I simulate, let me open peak current mode control. So we have peak current mode control over here now. And so if you see the difference between voltage mode control and current mode control, so let me show both of them at a time. So this is voltage mode control and this is current mode control. Everything will be same. Only here we'll be comparing IL with the reference and here we'll be comparing with the RAM, except that everything remains same. And so the implementation is very easy. If you implement one, you just have to make this inductor current and then you have to simulate. So if I go back, everything remains same. So power stage we are not touching. Only the controller block. I am changing the RAM to inductor current. So why ramp compensation is needed, I'll come back to that. So first let me and this is again PI or PID controller. So depending upon what values we give, either it can be PI or PID. So Banerjee is asking one question. Sir, how can we compare voltage and current? We are not comparing voltage and current. So what actually the MATLAB, that is actually a good question. So if you consider the simulation, both IL will be treated as a voltage and VCon is also treated as a voltage. So the MATLAB thinks both are the same. So MATLAB does not know whether it is a current or a voltage. MATLAB treats them as a signal. So to the MATLAB simulator, this is a signal and this is a signal and both are being compared. But in the actual circuit, what we do is, so let me go back here. So this is, okay, let me change the color first. So in actual hardware, what happens is you sense this current. So this sensor will convert amperes into voltage. So whatever current it sends, it will change into voltage. So maybe the sensor gain Kc will be say 1 millivolt per ampere. So for 1 ampere, it will generate 1 millivolt or maybe 1 volt per ampere. So the whatever sensor that we are using will convert this current into equivalent voltage. So it will convert into equivalent voltage. Now that voltage and this I reference is also in terms of voltage. So we'll be comparing two voltages. So even though we are showing that it is a current, but in the actual hardware, it is an equivalent voltage. So remember this Kc, we have a Kc and using this Kc, we will be deciding or designing the controller. So that's a good question. So we will be converting the voltage in current into equivalent voltage and then we compare. But in simulation, it does not matter, right? This is also a signal, this is also a signal. So in simulation, it does not matter and sorry, I reference. So for our representation, so as we are representing this as a current, this is actually a control voltage, VCon. But for our reference, we are mentioning it as a I reference. So although it is an equivalent voltage, it will be like this, right? So you can say this is IL sense. So you can say this IL sense and you can say this I reference. This is for our notation and for our better understanding. When you compare a RAM, you are mentioning this VR and this as VCon. So it makes you feel that you are comparing two voltages and here you are comparing two currents. But in the actual hardware, here also we are comparing two voltages. But for our better understanding, as we are habituated to this architecture and this is being used universal, that's why the notation is different. But it is an equivalent voltage. So this IL sense is also in terms of voltage, and this I reference is also in terms of voltage. But for our better understanding, we make it IL sense, so that then we can know that okay, this is a current mode control. That's why we use IL sense and here IL sense. So the same thing is being happened here. So now let me just simulate. Before that, let me close voltage block control, and I have changed the file name to op2. So let me just run it. So this is the current mode control. As I have told, it is not actually designed for current mode control. And sorry, one thing I forgot to do is we do not want derivative. So I'm making derivative to be 0. So I'm multiplying KD with 0. So now it is actually a PI controller. As for current mode, we need only PI controller. So I'm doing only PI controller. So Banerjee, you are able to understand, right? So now it is voltage, current mode control, and the step is from 1 ampere to 20 ampere. So accordingly, we can design the controller. Now, in fact, it is not properly designed. It is taking a lot of time, and there is also undershoot is also very huge. So we have to design it properly. So that is all about peak current mode control. Now, if you consider valley current mode control, it is also the same thing, except here it will change. So instead of plus, we'll have minus, and instead of plus, we'll have minus, and instead of minus, we'll have plus. So in peak current mode control to valley current mode control, what will change? So here comparator will change. So in the case of peak, IL is plus, I reference is minus. In the case of valley, it will be the opposite, and reset set pulse will change. That you can actually implement it, and we are not showing the peak current mode control currently, and we can move into the voltage, variable frequency. So if you have any doubts till now, you can please ask me. One student has a doubt. So how KPK values impact time domain process? So KPK values are the what you can say controller gain drop. So if you see the K loop will be GVD of S into some gains into GC of S. So depending upon the PI controller that you have selected, it will affect the K loop of S, and it will affect the overall closed loop bandwidth as well as phase margin. So bandwidth comma phase margin are dependent on KP comma KA. So if I choose very less bandwidth, then the transient response will be poor, and it will be slow. And depending upon the phase margin, the oscillations. So depending upon the phase margin, so whether the inductor current will go like this or whether the inductor current will go like this, so it will depend. So depending upon this, our transient response will be affected, and which are in turn dependent on KP comma Ka. So depending upon this, our transient response will be affected. So is that clear? Hello. 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 Am I audible?
Yes, yes.
Okay.
Yes, sir.
Okay. So Puranesh, is your query solved?
Yes, sir. Like
Okay.
I'm asking how this values impact practically. I want to like more explanation about KPK values, but it is yet covered because our design of controller is yet to covered.
Okay, or maybe one thing I can say. So depending
Okay.
upon how your eye reference is, say this is eye reference. Depending upon how your eye reference is changing, inductor profile will follow, right?
Yes.
So if eye reference is changing quickly, then inductor current is bound to change quickly, right?
Yes.
So how my eye reference is changing? Eye reference is the output of GC of S, which has KP comma KA. So if I increase
Yes,
the
yes.
KP KA values, then my eye reference will increase faster, and accordingly IL will change. But I cannot make KP KA increase very much, right? So there is a limit for KP KA. So depend. This is one way of saying, but the other way of saying, like more professionally or more theoretically, is bandwidth comma phase margin. So we will be designing the K loop of S to achieve certain bandwidth and phase margin, which decides the transient response. So this bandwidth and phase margin are frequency domain. So they are S domain, and they are also related to time domain. So bandwidth is related to rise time. So bandwidth and rise time are related. So if you if you achieve higher bandwidth, if bandwidth increases, rise time decreases. So rise time decreasing means it is reaching the transient like final steady state faster, and phase margin and eta, the zeta are related. So if you increase phase margin, then zeta will be increasing. So phase margin, if you increase, damping will increase. So if zeta is very less, it will be oscillatory under damped. So if you want more close to critically damped or more zeta, then you achieve phase margin. But the thumb rule is phase margin 60 degrees is good enough for design. So we'll consider say 45 to 60 degrees phase margin to have a better trade-off between zeta. So that is the thumb rule that we consider for our simulations.
Yeah, and I have another one doubt regarding that FSW by 10.
Yes.
This is the switching frequency by 10
by
is
10.
for controller bandwidth.
Bandwidth, yes, the loop bandwidth.
Yeah. Oh, for that period only controller will take action, or for entire period duration of
no, it is not the period.
by,
actually, if you plot the Bode plot, so if you plot the Bode plot, we want the bandwidth from the whatever bandwidth that we get from 3 dB bandwidth from the Bode plot, we want it to be FSW by 10. So actually there are two things. If you go by small signal approach, say if you go by small signal approach, the small signal itself has validity because we are neglecting the ripple information, right? So the model itself is valid till FSW by 10. So if you want to design it to say FSW by 5, then the model that you are considering to design itself is not valid. So you cannot actually design for this. Then you may ask me how to design higher bandwidth. So then there is something called large signal models where we actually consider the ripple. So one such large signal model is the what we call DT model. So this is called discrete time model. So I'm making it DT model where it is actually a large signal model that sir will be discussing in the upcoming week. So what is DT model, how to validate it using MATLAB, all these things are discussed. So let us move away from the controller design part. Sir, it is said that measuring IL is difficult in previous lectures, and another method is used to have IL from voltages. So actually whatever we will be doing from this, like in this course, I will be measuring IL using something called DCR sensing. So we'll use DCR sensing for measuring this IL, and that we'll be using for current mode control. For current mode control, we need the entire ripple. So our IL bandwidth of the sensor should be much higher, and whatever it should sense, it should contain the ripple information for the current mode control. So we'll be using DCR sensing. The sensing part we'll be discussing in the upcoming years. So yeah, we are sensing the inductor current, and we will be using it for the current mode control. I hope I'm able to understand. Like I hope I'm able to clear all your session, like doubts till now. So let us move to the variable frequency. So this is all about current mode control in fixed frequencies, but loops are there. Sorry, which loops are there? Can you please elaborate the question? Hello. Current and voltage loops. No, actually sensing is different thing compared to the loops. Sensing has got nothing to do with the current loop or voltage loop. So this sensing, whatever sensed voltage that IL you are taking here, that will be used in the current loop. So we are sensing to use it in the current loop. We need the current information in the current loop. That's why we are sensing this. Is this different from two loop control? No, this is actually two loop control. So we have two loops. We have two loops. One is the voltage loop V0 and the other one is the inductor current loop. So for V0, we are sensing V0, and for IL, we are sensing IL. So we sense both of them, and both will be used in the each of their loops. Did that solve your query? Okay, sir. Okay, so let us move on to the variable frequency quickly. So this is a constant of time. I don't know how to remove this top one. It is not going away. So this is constant of time current mode control. Sorry, voltage mode control, because we are measuring the voltage here. And I have discussed in the previous session that constant of needs minimum on time, and constant on needs minimum off time. So this is constant off time control. And why do we need minimum on time? I have discussed in the last session. I will be discussing again. So what happens is the control works like work in this way. So after constant off time, we assume that the voltage is lesser than the reference voltage. So during this on time, the voltage will increase, and at some point of time, it will cross the reference, and that will give a trigger pulse. So that will trigger the monoshot timer, so which generates constant off time. Now, what happens if this is V0? So that particular point is V0. So what I'm saying is, what if V0 is greater than V reference? So if V0 is less than V reference, it is increasing and it is hitting, then the output of this comparator will see a rising edge, and we are using a positive edge detector, which will trigger the monoshot timer. But if V0 is already more than V reference, the value is 1 and it will remain in 1, right? So now we have turned on the switch. So the on time is on, and when will this on time will end? Whenever this sees a rising edge, right? So if it is already 1, it will never see a rising edge, and the converter will be always 1. So QC will always remains high. So QC will always remains high, and monoshot timer will never be triggered, and Q remains always 1. Though the upper switch that in the buck converter, so this is the lower switch and this is the upper switch, right? So this will always remain on, and this will always remain off, and the inductor current will increase, and V0 will increase, and voltage and current will exceed. So when this situation happens, we need minimum on time. This has already been discussed in lecture 9. If you want more details, you can go through this link. The link I have embedded in the text. So that's why we need minimum on time. So how do we implement this in MATLAB? So what is the logic that we can discuss it here? So sorry, am I audible? Hello. Hello. Can anyone please confirm? Yes, sir. Okay, thank you. So what is happening? Audible. Okay, thank you. So what is happening? What exactly is happening is, our issue is if QC is if QC is going from 0 to 1, we don't have any issue. Monoshot timer will be triggered and it will work fine. But what if QC is always 1? Then we'll never see a trigger, rising edge trigger. So what we'll be doing is, say the monoshot timer gives constant off time, right? And then it will turn on. So this is a T off. T off. And since it is output gate, so this is monoshot timer. So monoshot timer will give us constant off time as we are inverting it. This is constant off time. This is actually going to the buck converter. So this is 0 and this is 1. So what we want is, whenever the QC is already 1, we don't want the switch to be turned on for infinite time. So what we want to be turned on for some time, and then we want it to be turned off. So whatever this time period is there, this is what we call T on minimum. So this is the minimum on time. So how we are doing this? So this is the circuit for minimum on time. So QC is, and this is OR function, right? So this QC rising edge is OR with something. So this is QC, right? So if QC is 1, then we need minimum on time, right? If QC is not 1, QC is 0, then output will be 0, and this entire wing has no meaning, and whatever rising edge that is coming, that will go to the QTR. Right, so whenever QC is 1, then only minimum on time is activated. So that is the first thing. So QC, we are doing AND operation here, because so whenever QC is 1, then only this minimum time. So this is minimum on time block. So this minimum on time block is useful whenever QC is 1. That is when we actually want. If QC is 0 and the switch is turned on, at some point of time, it will V0 will cross V reference, and QC will be going from 0 to 1. So if after minimum on time, same situation prevails. If after minimum, okay, let me first explain this minimum on time, then I'll come to your question. So what exactly we are doing? Let me change the color. So this is QM, right? So the output of the monoshot timer. So we are detecting this edge. So output of the monoshot timer, this is QM. So this is QM. We are detecting the falling edge, and this is actually a monoshot timer. This is another monoshot timer with input T on minimum. So this is another monoshot timer. So if I draw the same time period, so this monoshot timer will generate T on minimum. So this monoshot timer is generating this pulse. So now this is monoshot timer is generating this on time pulse. And then again, this will have a falling edge detector. So again, we'll detect this falling edge. So when you detect this falling edge, you will get a slight trigger, right? Now this is QFM dash. So from this monoshot timer we are using, and this is passed through another falling edge detector. So it will detect the falling edge, and it will come this. So this is a QFM dash. Now QFM dash is AND operation done with QC. So if QC is 1, then QF is, if QC is equal to 1, that implies QF is equal to QFM dash. So whatever QFM dash that we are getting, it will be QF. And whatever QC we are getting, we are doing the OR operation, and then it is going to QTR. So this will have a trigger, right? As we are doing OR operation, this will have a trigger. So QC will detect for a rising edge. If there is no rising edge, this will be 0. So if this is 0 and this is QF, then output QTR will be QF. So the output will see a trigger. So the monoshot timer is turned off here, and then we are forcefully generating a trigger here, which will generate the which will trigger the monoshot timer. So monoshot timer will be again on from here. So off time will be again turned on. So this is minimum off time, right? So this is T on minimum. So the monoshot timer will be triggered again, and so again if it is 1 here, here we have an inverter. So after on time it will be again 0. So what exactly we are doing is, to explain it in simple terms, everything depends on QC. If my QC is 0, then the output will be 0, and this entire block has no meaning. And when QC is 1, what is happening? No one is triggering this monoshot timer. So I am forcefully triggering this monoshot timer after T on minimum. So I am using this QM. So QM has turned off, right? So I am using this falling edge. I am delaying it by T of minimum time. And then I am generating this trigger pulse. I am giving it to monoshot timer. So when QC is 1, so QC is equals to 1 means V0 is greater than V reference. So the system does not have to turn on. The system has to turn off, right? So I don't want it to turn on for some amount of time. So I am giving it minimum on time, and then I am turning it off. Now you may ask me, So now I am turning it off for constant time, right? After this constant time also, if V naught is greater than Vref, what will happen? Minimum on time, and then it will turn off for constant time. Then again it will check if V naught is greater than V reference, then again minimum on time, and then it will be turned off. So until and unless V naught is less than V reference, this minimum on time block will be working. So one student has asked me, so what happens if this situation remains after this minimum off time as well? So until and unless V naught comes less than V reference, this minimum on time block will work. So now V naught is less than V reference means what? QC is equals to 0. So QC equals to 0 means the output is 0. So this minimum on time block is now is not affecting the final signal. So is this clear, or should I explain it again? Hello. If you have any doubts, I'll explain it again.
Yeah, explain it again, sir. This block.
Okay. So
A QM.
Okay, I'll explain. So
Yeah.
coming from here, so how my constant off time is working. Constant off time is working, say after constant off time, whenever I am turning it on for something. So my off time has ended. Now I am turning it on. So when I am turning it on, the condition, when will I turn it on? Or when will I turn it off? So this on time will end whenever V naught crosses V reference. So whenever V naught crosses V reference, it will generate a positive edge trigger that will trigger my monoshot timer. So at this point, my V naught has crossed V reference. Then I will turn off, and I'll maintain it for constant off time. And now V naught will be less than V reference. So I will turn it on. So now V naught will increase. At what point V naught crosses V reference, it will be turned off. So this is the stable operation. Now what I'm saying is, say I have turned it off, and now I am turning it on, but my voltage is already greater than V reference. And now if I turn it on, the V naught will be much more than V reference, right? So the off time will not be triggered. So off time will only be triggered when V naught is greater than V reference, and during on time when V naught crosses V reference. But before the start of on time itself, my V naught is greater than V reference. So V naught will continuously increase, and it will never trigger the monoshot timer. So it will never get turned off. The switch will not turn off. So under these circumstances, what should I do? I will turn off. I put some circuitry so that it will check whether V naught is greater than V reference or not. If V naught is greater than V reference, it will turn off immediately after a time period of T off minimum. So sorry, T on minimum. See, T on minimum. So it will check whether this condition is holding true or not. So whenever it is turned on, it will check V naught is greater than V reference. If so, then we turn on for minimum time, and then we turn off for constant time. Again, we turn on. We'll check whether V naught is greater than V reference or not. If so, we'll turn on for constant time, and we'll turn off until V naught comes less than V reference. So now we are turning it on again. Say now V naught is less than V reference. So we'll turn it on. And when it crosses V reference, then we'll turn it off. So whenever, so whenever it crosses V reference, then we are turning off. So for that logic, what we want, that positive edge is not coming from the closed loop. So what we are doing, we are trying to forcefully give this trigger from a circuitry. So what this circuit is doing, what this circuit basically is doing is, whenever this monoshot timer ends, so monoshot timer ends after constant off time, right? So after this, we are taking this edge, we are delaying it by some amount of time, and then again, so from this is the constant off time. So from this, we are forcefully generating a trigger after T on minimum, and that we are feeding it to the monoshot timer. So it will check whether V naught is greater than V reference or not. So if this is happening, then we are forcefully generating a trigger after T on minimum, so that monoshot timer will be triggered and off time will be started. If V naught is less than V reference, then the closed loop itself will trigger, and this block will not work. So I hope this is clear. Hello.
Yes, sir.
Okay, so the basic things you can remember is whether V naught is greater than V reference or not. If yes, then minimum on time circuit will work. Minimum on time circuit will work. If V naught is less than V reference, then minimum on time circuit will not work. As the switch is turned on, V naught will increase, and at some point of time, V naught will cross V reference and will get a positive edge. So the main motto revolves around this positive edge triggering. So positive edge. We need a positive edge. Either it will be given by the closed loop, or I'll forcefully give the edge so that the off time will start. So that is what you have to keep in mind. And if you want many further details, Sir has already explained in lecture 21 of the previous course. So you can go through this course where Sir has explained in detail. So this is the constant off-time control. So before going into digital PID controller, let me show the MATLAB simulation. We are still in the analog control. So the OP3 is constant off-time control. So constant off-time, Sir has to provide T of constant. So which is V in minus V naught by V in into T. So for buck converter, this is the off time. So that is coming. And on time minimum, that is user's choice. So Sir has considered T by 50. And I have to change this to OP3. And before going on to the simulation, let me show this is constant off time, right? Because it is peak. So peak constant off time is this one. So let me open it and let me show some quick demonstration. So again, everything remains same. The power stage remains same, only controller changes. And what is happening? If I come back to my circuit, this is voltage mode control. And in case of current mode control, we compare it with IN. So my V reference is subtracted, V naught is subtracted from V reference, which gives me V error voltage. It is going into PI controller. Now this is being compared with the IN. In the case of voltage mode control, we are comparing it with voltages, but in the case of current mode control, we are comparing it with the IL. So if positive edge is detected, then this is the monoshot timer. So monoshot timer has what? Constant off time. So this off time, so edge detection is rise. So whenever it detects rising edge, it will turn on and off time is started. So this will generate a pulse with one value for constant off time, and then it will turn off. But this is constant off time, and the NOT gate should be present at the output. As you can see, NOT gate, we are connecting the NOT gate and it is going here. And so does this circuit does not have voltage feed forward? No, this is current mode control, and current mode control has good line regulation. So we are not using voltage feed forward. So now that you have pointed one very good question, so let me say here. So voltage mode control, we use input voltage feed forward because it has poor line regulation. And current mode control, we consider something called load current feed forward to improve the output impedance shaping. So here the issue is poor line regulation, and here output impedance or Z out, output impedance shaping, Z out shaping. So, and also it will increase the transient response very fast. So this SAR will explain in the hardware. So SAR has implemented the load current feed forward, and SAR will show with current mode control without load feed forward and current mode control
Hello.
with load feed forward. Yes.
Are we? This is a general question. Are we
Yes.
accessible to this MATLAB files?
Yeah, actually someone has asked me. So as I'm a TA, I got this MATLAB files from the course instructor, but I'm not sure whether you can access this or not. So I
Because
asked you to, yes.
no, week 3 is like it's an interactive session. MATLAB sir is showing,
Yes.
and then he's explain. So it's like week 3. It's difficult to grasp
Yes.
because
Actually,
we
week
can
3 is
study
very
theory.
crucial.
So that's why I asked, like, if we get this, like, if analog fails also, guess we'll try it or something. No, so
Yes.
otherwise we have to start from scratch.
Scratch.
Is
Yes.
whether possible?
Yes.
And
I'll
in group,
talk to sir.
discussion group, no one like from the NPTEL there is no response. We are putting the questions, but we didn't get any response of
Okay.
any question.
Okay.
It's
Sorry for
just
the
just
inconvenience caused. I will talk to the TS
uh,
and I'll ask them to
yeah,
answer your queries. And
yeah.
you ask NPTEL group whether they can provide you with the
Yeah,
MATLAB
that
files or
we
not.
asked.
I will ask the
Yeah, we
I will
asked.
also ask the professor whether he can share.
Yeah,
The,
we asked actually. That's why I didn't get a reply. That's why I asked you.
okay, I'll
We
ask
asked
the
in that man.
professor. If he
Yeah.
can share, then he will be giving it to NPTEL, and we'll ask the NPTEL people to share to the people who has enrolled to the
Yeah.
course. But if he says no,
Okay.
then sorry, I will not be able to help you because it depends upon the
Okay.
course instructor whether it can be shared or not. But I'll request the uh, course instructor to share if possible, and
Okay,
I'll
fine.
get back to you now. I'll ask
It's
before
not
next.
like it's better if the lab earlier course like constant analog control. If it is preferable, also that's fine.
Okay,
Like any
I'll
of
ask.
one of the. That's why. Yeah, that's why I asked. Yeah,
Yes,
right.
I'll
Thank you.
let you know. So coming to this, so this is the monoshot timer. So if we can compare, so this monoshot timer is this monoshot timer. Now we'll enter this minimum on time block. So this is the minimum on time block. If you enter the minimum on time block, so here it is. Let me change the color. Make it green color. So we are detecting this falling edge, right? So this falling edge is this falling edge, and then this delay block is another monoshot timer. So the monoshot timer with T on minimum. So this is another monoshot timer, and it is having pulse duration T on minimum. After this T on minimum, there will be another here inside this block. There will be another falling edge. So this falling edge is this, and now this is AND with what QC. So this is QC. So we are ANDing with the QC, and the output is OR with the output of the rising edge. So it is OR with the output of the rising edge. So that's what we are actually implementing. So this is constant off time with minimum on time. So we have few questions. Sir, discussion is about feed forward terms. Please discuss about feed forward terms. Sorry, I got deviated. So in voltage mode control, we need input voltage feed forward because it has a poor line regulation, and in current mode control, we need load current feed forward to shape the output impedance in a better way, and also to improve the transient response will be improved significantly. This sir will be showing the hardware results, so where you can appreciate the advantage of load current feed forward. But for load current feed forward, we have to sense the load current. So you have to have the provision of load current sensing, and then only you can use the load current feed forward. But without load current feed forward also, we can have a good transient response, but in the presence of load current feed forward, the transient response will be superior and it will be much faster. And again, there will be less than a minute. So if this meeting ends, please join in so we can continue our discussion. So this is the overall implementation of constant off time control. So now this constant off time has minimum on time as well. So let me just simulate. So we have OP3. So let me just simulate it. I'm running it, and let me see the output, sorry, inductor current response as well as output voltage transient response. It is simulating. Let us give it. I hope my screen is visible. Hello. Is my screen
Yes, sir,
visible?
visible.
Okay. So this is the constant off time control. So it has constant off time and with minimum on time. So let me do one thing. So let me change the gain. So I have simulated OP3, right? So I have simulated OP3. So it is constant off time. Let me change the gains to say 60 and see how it is responding. So now I'm increasing the gains to see how the response is changing, and let us see the response. It is taking some time to simulate.
Sir, in the previous discussion we had like a current feed forward and voltage feed forward.
Yes.
Does those comes under closed loop control? Like feedback mechanism is
Yes.
there or not?
So yes, feedback mechanism is there, and on top of that, we are adding this feed forward. So to improve the transient
Feedback
response.
mechanism in the sense output voltage is sensed with compared with the reference. That's the thing.
Yes, yes, yes. So on top of that, we are having this. So now if you see, I have increased the gains, and let us see the transient response. Now it is trying to reach somewhat faster, right? So as you can see, now let me increase the gains further. Maybe let me make it 100 and let me make it 100, and let us see. So if you remember in the previous sessions, I have discussed like let me go back. So for constant off time is constant, on time is variable. So I have told that step up transient is superior. So if I give a transient like this, I told the inductor current can go like this. But this transient response again depends upon the controller gains that you have used KPK. So if I am using higher gains, then the bandwidth will be high. So I am checking whether it will achieve something like this or not. So this is what I'm trying to see, whether I can achieve this in constant off or not. Similarly, in constant on time, we'll check the step down. So step down will be superior. So the inductor current should follow like this. So this I will not be showing. I will be only showing the step up response. So let me check if my MATLAB is still working. So you have to remember this. So constant off time means on time is variable. So load step up is superior, and constant on time means off time is variable. So load step down is superior. So this you have to keep in mind, and I'm trying to show you this response, whether it can achieve this or not. So I think it is
There
taking.
are all these under dynamic conditions, right? If we have the reference changes frequently, then the uh, uh, switching frequency FSW will vary, right?
Yes, yes, yes. And this is variable frequency. So depending upon the load current and everything, the switching frequency will be set at that
Yes,
particular
sir.
value.
Here, like we reference how it gets changed.
No,
Sir.
no, this is I not. I am talking about load current feed forward, not load current transient, not feed forward, not reference transient. So there are two things you have to take. One is load transient, and another one is the reference transient. So whatever I am showing, it is a load transient, not reference transient.
Sir, reference changes based upon the load or not?
Yes. Say if like whatever load that we have connected, say this is a converter and it is connected to some load or some IC, say. Previously, say the IC is working at say 1.5 volt, but now it needs say 3 volt. Maybe it needs, so then the converter has to provide this say 1.4 volt 10 amperes it is needed. Now it needs 3 volt 10 amperes. So current is same, but reference is changed. Maybe from 10 ampere to 15 amperes also it changes. So there is both load transient as well as reference transient. So that's why we consider load transient as well as reference transient.
Sir, reference in the sense you are talking about the voltage, and the load in the sense you are talking about the current, right?
Yes, yes.
Are they all fixed, sir? Like
Yes,
any
actually it can be
normal?
dynamic, but we are considering for our better understanding, we are considering from a fixed value to another fixed value. But in actual reality, in any product that you use, it will not be fixed. So it will be continuously changing. It will not be dynamic. So accordingly, the load has to change. So we usually take a step load to like compare. So this is a reference. So we consider it for a step response, and then we'll see whether it is stable or not. So it has run. Actually, it took some time because of the high processing. And if we see now, the response is much faster, and I think it is reaching very fast. If you see, I have given the very high gain. So because of that, it is going in the way I am telling. But again, these are very high gains. So this is for simulation. We have to check whether this is practically feasible in the hardware. Or so this
Hello.
is just to show. Yes.
There is one in I think week 2.
Yes.
There'll be for constant on time is better for step down, and constant
Yes.
off time
Yes.
is. Can you say that reason? I forget it. Like, can you
Okay.
just recall on that?
Okay. Okay. So I'll be using this space. Okay.
Okay, fine.
Okay. Maybe I'll use a very light color. So we are discussing about constant on. You can see, right?
Yeah, yes, yes, yes,
So
yes.
constant on, if you consider off time is variable, right? Off time is variable. So off time is variable. So it can be turned off for like longer amount of time. So if you consider a step down transient, what we want the switch to be turned off for longer amount of time, right? Isn't it? Hello.
Yeah, yeah, yeah. Yes, yes,
So
yes.
now
Okay.
it is off for longer amount of time because off time is variable. So the step down
Hmm.
transient is superior.
Hmm.
If you
Okay.
consider constant off time is constant and on time is variable. So it can be turned on for a few cycles, which I have just shown. So if you consider a step up load transient, so it can be
Okay.
turned on for many cycles. And this is a like fastest case. So it is going in like one switching cycle. But again, it depends upon what are the KP, what are the KI. So depending upon that, the speed of the response will and we
Okay.
decided.
Okay.
So this is a step up trend here. So now
Okay,
you
fine.
may
Sir,
ask me, yeah,
sir, superior you mean that it is reaching the steady state faster.
yes, superior means it is faster compared to like compared to constant on time versus constant off time. I'm see if you consider sorry. So if you consider constant on time, so on time is constant and it will have minimum off time, right? So minimum off time. So if you consider step up transient, like off time cannot be zero. So what happens is it will turn on for constant on time and minimum off time, constant on time, minimum off time, constant on time, minimum off time, and then it will reach. So if you compare
Understood.
these two, we can say that right one is faster because there is no off time, no off time here, because here on time is variable. So on time, but here on time is fixed, off time is variable, and we have discussed in the previous slide that there should be something called minimum off time. So because of this minimum off time, the step up transient will be not as fast as this constant off time. Similarly, if you consider step down transient here, so off time is constant and on time is variable. So minimum on time off, sorry, minimum on time, constant off, minimum on, constant off, minimum off. So this is minimum on time. So constant off time step down transient is not as fast as constant on time step down transient. So that is a trade-off that we have to because of this minimum on circuit here, sorry, minimum off circuit here and minimum on circuit. So this will make the transient response somewhat slower, but it does not mean it is slow. We are comparing both of them and we are saying it is slower or faster. It is not slow or fast. We are comparing whenever we are saying it is faster, we are comparing this with the its counter constant on time, and when we are saying this is faster, it is compared to its counter constant off time. So that's why this is the advantage. So here it has fast step down, here it has fast step up, and that I have shown here. So I can achieve faster step up, but I can tune properly again, so that voltage will also be somewhat faster, but tuning part let us not discuss now. So this is all about analog control. So now before we move into the digital control, I'll be discussing something called digital PID controller. So in analog PID, we are implementing using op-amp, right? So in analog, we are using op-amp based implementation, but in digital, we are using FPGA. So it is a code, right? So we have to write in terms of code, Verilog code, but Verilog code part will come in the upcoming weeks. But let us look at the logic. So what is the logic behind the PID controller?
Sir,
So
I have one doubt. Like
yes,
for op amps and all, you are using this control, you are using digital. Then why can't we implement whole circuit in digital domain, like
yes,
without using
yes. Uh,
hardware?
with no, like, see, the power stage and the controller stage. So this is the controller, and this is the power stage. So power stage is analog. This is analog, and let me change the color. And this is digital. So what we are trying to do is we are taking everything in digital, and the circuit is analog. Circuit has to be analog, right? So that's why we are putting this in analog and this in digital. So we are taking everything in digital, not just controller. We are it will have comparator is in digital, RS flip flop if you want, it is in digital, V reference minus V naught. All these things, everything will be in digital, and the rest of the part is analog. Have you understood?
Yes, sir. Why can't we implement that power circuit in digital too?
That is like, let me come back there. So if you consider buck converter, so this is the input stage, and this is the inductor, and this is the output capacitor, and this is the load. So load is external world, right? So load is in the external world, and this inductor cannot be implemented because depending upon the size, it cannot be implemented in the IC. So inductor will stay outside. So this inductor is also in the outside. So what people do is, you see this part, right? So this part is in an IC. So we use this part in IC. So not actually input voltage. So input voltage will be coming here. So we use switches in IC, inductor outside, capacitor outside, and load is also outside. And input voltage we are giving it from the outside. So to the maximum extent that we can digitize the circuit, we will be digitizing. But other part, it should be in the on the outside. Inductor you cannot put in the IC, it will be very difficult, and there will be a restriction also. Say if I want 1 microhenry, that cannot be put in IC. So IC can make very less inductance. So inductance in all the commercial products, inductor will stay outside, and only the switches will be inside.
Yes, sir. But digitally, like we can implement the inductor too, right? Like,
how can you implement inductor in digital? Inductor is a component, right? So whatever component that we are doing, it should be physically available there. So whatever switch that we are doing in the IC, there will be a switch. So they will make a switch in the IC, and similarly, switch will have capacitance, but that capacitance, there will be a limit. It cannot be a very high capacitance. So an inductor is a component, so it cannot be digitized. Right? How we cannot digitize inductor? Inductor
like
is a
we can
component.
mathematically model and can't we implement it digitally, sir?
So you can mathematically model, then it will become a simulation. It will not be a hardware, right?
Okay.
Let me erase this because I'd like to discuss something else in this slide. So whatever we can digitize, we will be digitizing controller side, and it will be an IC digitized, and we are implementing in the FPGA, and switches will be IC. So so everything is becoming IC nowadays. So whatever we can make into an IC or is available, that will be used. So digital PID controller. So digital PID controller, it has proportional part, and it has integral part, and it has digital part. So this is the condition. So VC of n. So VC of n is Kp into V error. So this is V error. So Kp into V error plus Ui of n. So this is integral term. This is integral term, and UD of n, and this is derivative of term. So Ui of n means what? So Ui of n will calculate. So Ui of n means it will take the present error plus previous integral. So integral term will have previous term, right? So previous term. So Ui of n is nothing but Ki into V error of n plus Ui of n minus 1. So now we are going into digital. So in analog, you write V con of t. So it is varying with time. But in digital, we write V con of n. So at nth instant, what is V con? At n plus 1th instant, what is V con? So we'll write in terms of n and n minus 1 or n plus 1. As integrator, we'll have previous term. So it will be Ki into present error plus previous Ui of n minus 1. Now, derivative, what does derivative do? It will take the error difference, present error minus previous error. So this is previous error. So like this is how digital PID work. into KD. So if I apply Z transform in this equation ui of n, so we will get ui of Z is equals to Ki into VE of Z plus Z inverse into ui of Z, right? So if I bring this Z inverse, we'll get 1 minus Z inverse is into ui of Z is equals to Ki into VE of Z. Now if I consider only ui of Z, it will be Ki by 1 minus Z inverse into VE of Z. So this is equation 1. Now you consider ud of n and apply Z transfer. So ud of n is equals to Kd into VE of Z minus Z inverse into VE of Z. So if you bring ud of Z, so ud of Z, it will be Kd into 1 minus Z inverse into VE of Z. So now if you take Z domain, like Z transfer function here, you will get VC of Z is equals to Kp into VE of Z plus ui of Z plus ud of Z, right? So we know ui of Z and you know ud of Z. So now if you back substitute this equation 1 and equation 2 here, so substitute equation 1 comma 2. So what will you get? Let me change the color to say violet color. Now you will get VC of Z by VE of Z is nothing but Kp plus Ki by 1 minus Z inverse plus Kd into 1 minus Z inverse. And what is VC of Z by VE of Z? It is GC of Z. So this is the digital PI controller and this is the equation. So this we are getting from this and that's how you are implementing. So Ki by 1 minus Z inverse is what? Ki gain, and this loop will give you 1 by 1 minus Z inverse. Because it is a negative, positive feedback. So it will be having minus, and the feedback gain is Z inverse, and the forward gain is 1. So it is 1 by 1 minus Z inverse into Ki. So this is proportional, this is integral, and Kd we have 1 minus Z inverse. So it has a feed forward term with the minus. So this loop is 1 minus Z inverse into Kd. So this is derivative. So we have Kp plus Ki by 1 minus Z inverse plus Kd into 1 minus Z inverse. So this is the digital implementation of the PID controller. So how do we implement this in MATLAB? So Z inverse, for Z inverse block, we consider a register. So what you want, this is ui of n minus 1, right? So what we do in the MATLAB, we use some register which will hold the value. So which will hold the previous ui of n minus 1 value. So we use a n minus 1. So this register will have 1 cycle delay and it will hold the previous ui value and it will be added in the present value. So here we have one register. So Z inverse, we have here one register, and here also Z inverse, we have one register. So what we are actually doing, we are taking the previous value, storing in a register, and we are using in the next cycle, which will actually give Z inverse. Z inverse is nothing but unit cycle delay. So in digital domain, Z inverse means unit cycle delay. So we use a register which will store the value of the previous cycle, which will be used in the present cycle. So as I have derived in the previous slide, GC of Z is nothing but Kp plus Ki by 1 minus Z inverse plus Kd into 1 minus Z inverse. If you elaborate it, it will be Ki Z by 1 Z minus 1 plus Kd into Z minus 1 by Z. And if you take common and add all of these things, you will get this final expression, which is Kp plus Ki plus Kd to Z square minus Z into 2Kd plus Kp plus Kd by Z into Z. So this is just to make you understand the physical, the mathematical derivation of GC of Z. So in analog control, we know it is Kp plus integral 1 by t into integral K dt plus K dt plus Kd into derivative d Ve of t by dt. So this is in analog domain, and if you take S transformation, you will get Kp plus Ki by S plus KDS, ideal transfer function if you do not consider any tau d. So this is converted to this. So you can say S in S domain is equivalent to 1 minus Z inverse in S domain. So Kp plus Ki by 1 minus Z inverse plus Kd into S, Kd into 1 minus Z inverse. So this is the analog expression for PID controller GC of S, and this is the digital expression for GC of Z. Since it is Z domain, digital, we have Z transform. Since this is analog, we have S transform. So this is the basic implementation of digital PID controller, and we'll implement this in MATLAB as well. So that is a building block. So we have discussed about analog control and MATLAB implementation. It will be exactly same in the digital control, except it has few building blocks like ADC. So we have to convert V0 to VN. So we have ADC, and then we have digital control. Digital controller GC object in which is like digital, and then if you want DAC, you will be having DAC. So all these things comes in the digital control, but the controller gains everything, whatever blocks we have used, power stage, everything will remain same. Only some additional blocks will be needed. So that's why we are discussing about this additional blocks implementation in the MATLAB. So let me come to the digital voltage control. So let me check. Divya, are you able to understand what we are discussing? Hello, Divya, are you there? Okay. So I hope everyone is understanding. Digital voltage mode control architecture we have discussed in the last week as well. So what I will be discussing now is just a MATLAB implementation. So in digital voltage mode control, the only change is here we have analog to digital converter, and the GC of Z is digital controller, and it is being compared with the ramp, which is a counter. And then comparator is in digital, and the flip-flop is also in digital, and we will be trying to implement this in digital. So let me move back to MATLAB. So I think this is in which lecture? This is in lecture 25. So I'm going to lecture 24, 25. Let me close this. So Sir has made everything in a similar fashion. So what I'll be doing is I will be accessing the main file. PID controller, let us not go into the design part. Let me open the voltage mode controller. So again, is this trailing edge modulation or leading edge modulation? It is trailing edge because set is being done by FSW. So that's why it is trailing edge modulation. And whether it is interval 1 sampling or interval 2 sampling, how do I say? We have to check where the sampling is happening. So as I told, we will not sample exactly at this point because there will be noise. So we'll sample just before this. So the sample is being taken here, and this is interval 1, and this is interval 2. So this is interval 2 sampling, and we are considering 1 cycle delay. How can I say that? Because the V0 of n taken in the present cycle is used to generate VC of n in the second cycle. So there is this 1 cycle delay, and this is interval 2 sampling as well as trailing edge modulation. And this is in the lecture 25 that Sir has discussed in the present course. So let me move back to the simulation. So
Excuse me.
Yes.
Sir, here is you are saying that it is taken in the interval 2 sampling.
Yes.
Like, why can't I take in the interval 1 sampling?
Yes, you can take
there,
interval 1 as well, but usually in the commercial products, people take 1 cycle delay, which is
yes, sir. Yes, same 1 cycle delay.
you can take here
saying
also.
that,
You can take here also.
but
Sorry.
why you are saying exactly interval 2 sampling?
No,
Just I am confused.
yes,
Here
like,
it is
it
at
can be
the
interval 1
interval
sampling as
range.
well. So depending upon where you take the sample, it will be decided. So we usually take it before the FSW. So it is in interval 1, 2. If you want to take after the FSW, then it will becomes interval 1 sampling. So this is just a notation of interval 1 or interval 2 sampling. So it depends where you are taking the sample.
Yes, sir. But if that is the case, then the FVD must be taken before, right?
Yes,
Like,
yes. Actually, this will be before. For while we are talking, we say that we are taking the sample, like this is theoretical, right? So we say that we are taking sample at this point, but in the actual hardware, we will not take here. We'll just take sometime before this. So it is being sampled in interval 2. That's why we are saying interval 2 sample. Understood?
yes, sir.
So let me come back to digital voltage mode control. So if you see here also the power stage remains same, only the controller is changed. So controller, it has, as you can see, it has like new blocks here. So let me use annotation here. And let me use red color. Let me know, can you see me drawing here? Hello.
Yes, sir, able to see.
Okay, okay. So I'll be using this and I'll be drawing here. Sorry. Wrong. So you can see this, right? Event trigger ADC. So what this is doing is, so this is working like an ADC. So this entire block is working like an ADC. So V0 is entering and this will be V0 of N. So what exactly are we doing here? Let me go inside. So let me stop the annotation and let me go inside. So inside, first let me erase this, annotate, erase. And let me go inside. So this is what here we are getting the input, right? So this is V0 and this is ZOH means zero order hold. So it is holding the value. So when is it holding the value? So it has one trigger. So whenever it sees a trigger, say the waveform is like this and trigger is coming like this. So whenever, sorry, this will be very small. So whenever this trigger is coming, it take the value, it will hold. And whenever the next trigger is coming, it will take the new value, it will hold. And whenever the other trigger is coming, it will hold. So the trigger says when it has to take the value and this block is enabled. So enable means this will work. Enable equal to 1 means it will work. Enable equal to 0 means it will not work. So why we have put enable here? We have put enable here because if you go into the actual circuit, people will not use ADC all the time. And when they are not using ADC, they will turn it off to reduce the power. But here we have put enable always on, so our ADC is continuously working. And our ADC has one FSW. So this FSW is uniform sampling. Because this is fixed frequency, we are using uniform sampling. Fixed frequency. And if I go into the block, what I have, so this is the sampling frequency. So I am sampling it once in a cycle, switching frequency, and you can insert phase delay as well. So TS is the delay, and it can be inserted from the code. So there we can define TS and we can insert that. So what we have here, so we are discussing about the ADC block. So this is ADC and so we are discussing about this ADC block. So we know that ADC block has one trigger, which will trigger the point at which the sampling has to be taken. And since it is fixed frequency, we have given a fixed frequency pulse. So it will take the sample uniformly, and that is why this is uniform sample. So now this is V0 of N. As you know, like, yes.
Sir, inside that event trigger ADC,
Yes.
we are giving constant term the switching frequency to 2 blocks, right?
Constant.
And inside that event trigger ADC, yeah.
Yes.
Yeah, these 2 blocks, whether it is available in the MATLAB, sir?
Yes. So this is enable. This is enable, and this is trigger. So I'll show you. If I do enable, and I click. Sorry. If I click enable, so this is enable block. You have to keep it inside, and this is what is the trigger block. So trigger block. So you have to create a subsystem. This is a subsystem, and you have to put trigger and enable, which will automatically show 2 input signals, enable and trigger here. Or if the main basic idea is it has to be inside a subport. So that's why you have to create a subblock, and then you have to, maybe I can say
That zero order hold is also a block, right, sir?
Yes, so zero order hold is also a block, and this is the block. So by default time, make it a -1, and so -1 is actually default, and this is actually driving or deciding when I have to take the sample. So you keep it as it is. So what you can do is
Zero order hold is used for sampling or reconstructing, sir?
sampling. We are using the zero order hold to take the sample, and it will hold it for that amount of time, for that until the
So
next
what
sample.
happens if we use first order hold?
So zero order hold, let me annotate. So we are using zero order hold because it will hold this. It will be holding like this, and it will go like this. But in first order hold, it will be linear. So it will be linear, and then again it will go linear, and which makes it complex. And we use zero order hold because we want it to be constant. So that's why we use zero order hold. And how do we do this in Verilog? That we'll check when we go into the Verilog simulation. So now we have discussed the ADC part. So let me annotate it again. So this is ADC part. So we have got V naught of n. Again, we are saying that it is a digital signal because it is constant, but MATLAB sees both analog and digital as a signal. So we cannot differentiate in the simulate, but when we go for hardware, then we will be able to see actual digital and analog signals. So in simulation software, everything is same. Both analog and digital are signal to this simulator, but it is for our understanding, I'm sure. So now this is a V error of n. So V error of n is going into digital controller. So this again block is a digital controller. It also has a trigger signal. So let me go inside this digital controller. So I'm going inside this digital controller. So again, digital controller has three things. One is KP, one is KI, and the another one is KD. So let me go back to my thing. So KP into V error of n. If you see here, we have V error of n, right? So KP into V error of n, and then UI of n. UI of n is what? Ki into V error of n plus UI of n minus 1. So this is, let me draw, then it will be easy for you. And let me change the color to red color. So this output is KP into V error of n. And this part is UI of n. And this part is Ki into V error of n. And this part is UI of n minus 1. So what we are,
Hello.
yes.
This controller, the reference also will be digitized, or like will
Yes, reference is also digitized. But in
is
Simulink, you
there,
cannot see the differentiation between analog and
no,
digital.
there is like one called housekeeping technique.
Yes, housekeeping means
So
like their
we'll
reference is in,
program the
yes.
reference. So
Yes.
we
Housekeeping means only reference is in digital, everything is in analog. But we are talking
analog.
about actual digital. So controller output, error, everything is in digital.
Maybe it's like out of box. Like if we program that reference and we use this implementation digital, whether it will work.
Sorry, can you please repeat? Your voice is low.
No. Hello.
Yes.
Now it's okay.
Yeah.
The housekeeping I understood. Okay, that is fine.
Mhm.
Now the reference will give constant value. Instead of giving a reference constant value, we'll give a programmed reference and then we'll give
Yes.
this
That also
digital.
you can do.
It will work here, no?
Yes. So
Okay.
whatever you are saying, see here, a reference voltage is where. Exactly.
Yeah. This VREF.
Sorry. So
So
here the V reference is here, right? We are actually giving a constant V reference, but now that you have
instead of
pointed
VREF,
one
we'll
good
get a
question.
programmed.
Yes, you can give programmed. But if you see an actual IC, any IC, it will have something called startup circuit.
Okay.
So they will not give, say, V reference is 0 volt. They will not give direct 0 volt, because if you directly give 0 volt, V naught is at 0 volt, right? And V reference is at 1 volt. So the error is at maximum. V error is how much? 1 volt. So there will
Maximum.
be a spike in the controller output. So usually they will not
Okay.
give it like this. So one startup circuit I'm telling, what they do is they'll slowly increase the V reference. So this is V reference. So
Okay.
they'll start at 0 volt and they'll slowly increase. So this slope is say K RAM. This also will be decided and then it will go. So initially it will start from 0 volt. Slowly they will increase the V RAM and then they will go to V volt. And the slope will depends upon within how much one cycle you want. Say I want within 2 milliseconds. Then the slope is 1 volt by 2 milliseconds. That is the slope of their V RAM. So
So
this
that
depends.
will be the VREF. 1 volt by 2 millisecond will be your VREF.
Ramp, slope of the ramp.
Okay.
So we reference
Okay.
they're increasing in terms of ramp so that there will not
Okay.
be very surge in the output controller output. So like a smooth startup. So people will have different startup logic. So this is one of the logic and
Okay.
like
This is for reference startup logic. Reference, they will keep the
say the
startup.
converter is at open. Now the converter is 0 volt. It has to go to 1 volt.
Okay. Okay.
So we'll
Okay. Okay.
slowly increase. So it will
Slowly
smoothly
increase
go. Yes,
the.
yes.
Okay.
We don't want the
No,
error to
this
be 1 volt.
this
This is
this
used.
startup is used like in the for reference setting
ICs.
or like without
In any
ICs.
IC, if there is any IC or if any commercial product, again, there is less than 1 minute. If the meeting is ended, please join. So in any
Okay.
commercial product, say the IC is off, you have turned on the IC. Say you have considered your mobile itself. Mobile inside there is a buck converter, multi-phase buck converter. So in
Okay.
like when it is in the sleep mode, no, nothing is being done. Say it is at its low P naught operation, and when you
Okay.
click or turn on the phone,
Phone.
then it will trigger some and it will have to turn on. Say you are again opening a game or you are opening any
Okay.
browser,
Okay.
it needs some current. So a buck converter has to
Okay.
give some INO. So it will not
Okay.
directly do. This is one of the startup logic. This does not have to be the only startup logic. So they'll make the startup logic in such a way that it will be smooth.
Okay. It's not affect the full system, so that they will put a start.
We are in the MATLAB. So whoever was asking that out, so in the case of like if you consider a mobile, so it has some
Yeah, that
well,
I cleared. I cleared.
yes,
I got it. Yeah. Yeah, I can continue with that. Yeah.
yes.
What is this housekeeping?
So
That
housekeeping
I watched the
is
video, but I didn't get.
so housekeeping means say we have this V reference plus minus V reference and V naught V error, right? So if you put an ADC here, sorry DAC. Okay, let me erase and draw it. So if you put a DAC here, and if you give V reference in digital, so now you can program the V reference. So output will be analog. If you do this, they call it housekeeping because you are putting the what I call all the entire circuitry in analog, only small part is in digital. So this is called housekeeping thing. But if you put everything in digital, say V reference is digital, V naught is digital, everything, then we call it digital. So it is just a name. So when we say housekeeping, only reference is in digital, entire thing is in analog. We can change the V reference. So that flexibility we have. Did that clear your query?
Yes, sir, clear.
Okay. So let me move on to the digital controller. So what I was drawing, so I was drawing this thing. So this is Kp into V error, and this is Ki into V error, and this is Ui of n, and this is giving me Ui previous. If you see, this is Ui previous, so Ui of n minus 1, and similarly, this is V error, and this is V error previous, V error minus 1, and this is V error of n. Now this is Kd into V error of n minus V error of n minus 1. So if I go back to the presentation, so whatever equation that we are discussing, so whatever equation that we are discussing, Kp into V error of n minus 1, so Kp into V error of n minus 1, we are getting here Kp into V error of n minus 1. And if you see the other term ui of n, which is ki into v error of n plus ui of n minus 1. So that we are getting here. So this output, and the other part ud of n is kd into error difference. So the other part is kd into error difference. Now the entire summation is going into v call. So this is the entire PID controller. So this entire part is the PID controller, digital controller. The output is the V controller. Now let me come to this part. So I know that I am getting V error of n. How do I generate V error of n minus 1? So there is this circuit. This is actually a memory block. So if you go into this and if you search memory block, this memory block will come. So why do we need a memory block? So at the starting of your simulation, you do not have error previous, right? You only have error. So during the start, we'll give some value, say some random value that will be considered as error previous. So what this block does is it will take a sample of error, it will hold. So which we can use in the next cycle. So if I go inside this, there is nothing. Whatever input is there, the same is going into the output, but we are actually holding the value. This is a memory block, right? So it will hold the value. So this is the trigger signal that is coming. So whenever the trigger signal is coming, output voltage is sampled, and that sample will be held until the next cycle. And that next cycle
Sir,
is
why don't
error
you
previous.
use zero order hold here?
We can use zero order hold, but it is not mandatory because that memory block will save. But whereas in this case, we are not using memory block. That's why we are using zero order hold.
Can we
You can
use them interchangeably?
Yes, you can do that. You can do that. You can use the same block
Okay,
here,
sir.
but as it is not required, we are not using. So this is V error previous. Same thing with the UI error. UI error, UI previous is also the same thing. It has a trigger signal. It will be sampled, and that value will be hold, which I will use in the next cycle. So from UI, I am getting. So let me
Hello.
clear this. Yes.
Why we need a V error previous here?
So
Only V previous.
yes.
Enough, right?
And let me just clear this, and I'll explain.
Yeah.
So if I delete everything, so why do I need error previous? If you see digital is derivative, right? So it is a difference between the error. So V error of present value minus V error of previous value. So that's why for derivative, we are subtracting V error, and V error minus V error previous, that is going into the KDD. KDD is the digital KD value. So for
This
integrator,
can you just
UI
open
previous.
the
For derivative,
subsystem?
we error. Yes.
Okay. Can you
And
just open the subsystem and
this one. Okay.
what is?
So
Yeah.
here, whatever input is there, we are giving it to output, and there is enable and trigger. So trigger means whenever this trigger comes, then only this subsystem will work, and that value will be hold. This memory block will be used to hold the memory of the previous value. So initial condition I have put 0, and
This trigger signal is same as like sampling switching frequency or
sampling,
like.
and it can be different. So here I think
Okay.
SAR has used the same thing. If you want to use a different one, you can use a different one. So it
Like
is up
this
to your
decide
choice.
like the values is decided how like what is the fact that will be upcoming lectures we will decide or like
Which values?
uh, like the sampling values. Okay, generally switching period will sample,
Yes,
but
yes. If you want,
accurately for
so if you
each
want,
any application.
yes,
Wait,
exactly.
1 second. I'll complete my question. Then I can
Okay,
uh, like this for particular application this amount of sample. Like how can we determine or decide like we'll apply the samples
okay. So
sampling like that. I think free come upcoming course it will come or like
yes, it will come.
this is
So if
like
you
a
want 1 cycle delay,
it's a,
so you will take
uh,
sample once in a cycle, and it will be used in the next cycle. And if you want TS delay,
okay.
you have to take the sample TS time before. So depending
This
upon your requirement,
that
you will take.
TS time is determined by like that is a random value or like we'll
Uh,
that is also determined by some calculations are there like
yes,
mathematical proofs are there to decide this delay
yes.
or like I'm
So
asking.
TS time is ADC conversion time plus
Yeah,
FPGA computation time.
computational time.
So if
Yeah,
your
okay.
ADC is slow, then your TS has to be high. If your ADC is fast, then TS can be low. So depending upon that, TS is decided. So what we want
So
to do is we'll have to provide the digital controller enough time. So it will take the sample and it will compute the reference. So that enough time we have to provide, and whatever commercial products are concerned, they will take 1 second delay. So they will get 1 second delay for ADC conversion plus FPGA computation.
Okay, fine. Yeah, fine.
So this completes the digital controller. Now for RAM, you can let me take the annotation. For RAM, we usually use counter, right? But for the simulation purpose, we are not using counter. We are using the normal RAM that we use in the analog. So if it is counter, it will have some effect on the transient response. You can consider that as also. But for simplicity, we are using normal RAM, which is analog signal. So this is analog. So this is analog signal, and here I am getting V control voltage. So if I go back to my voltage mode control, so I am getting this V control voltage from the digital controller, which I am comparing with the RAM, which is supposed to be counter, but for simplicity, we are using analog. Now this will give reset signal, and set is coming from this loop. Again, this is Boolean, and this is double, so flow double. So for data type to be compatible, I am using data conversion. So SAR is using data conversion to convert double into Boolean. And this is switching frequency. This is constant fixed frequency. So SAR is using another block for fixed frequency. So if I compare with the analog, so what extra blocks I have? I have this sampling ADC extra block and the digital controller extra block, except that everything is same. But since this is a simulation, both the digital and analog signals are treated as the same signal. Like simulator will not see any difference between analog and digital, but when we go into Verilog, then we will see the difference. Digital will be separate, analog will be separate. So let me run this program. So for these KPK
Hello.
that SAR has chosen, and I am running. Yes.
Sorry for the interruption.
No,
If we go to that Simlink
yes.
block, yeah, we go once. Yeah, in that FSW2 is there no in digital
Yes.
controller.
Yes.
Yeah, in that time period is same as
Switching
our
frequency.
ADC's time period or
Yes.
sampling time period. Let's say.
Yes.
If you have to implement some computational time in that, how to implement that? Because we are taking FS1 and FSW1 and FSW2 are same. Yeah, my doubt is like if you sample at that point of FSW1, let's say, how to incorporate our computational time in that?
Yes. So in this simulation, there is one option called delay, phase delay. So TS.
Yeah.
So
Yeah.
TS delay means it will be delayed by TS. And if you consider set pulse, this is the actual switching frequency. So in actual switching frequency, there is no delay. And in switching frequency, there is this delay. So you can use this TS where which SAR has mentioned in this simulation, and 0.90 means okay, let me draw it again. So this is FSW. So this is FSW. This is FSW switching frequency. And if I'm writing FSW1 or say F sampling, it is having the same frequency, but it is 0.90
delayed.
0.90. So if I see, I am actually 0.1 T delay between this and this. Is it? The sample I am taking here is being used in this cycle. So this 0.1 T is the sampling delay, TS.
Yes.
So,
my doubt is like here we are sampling at 0.90, let's say. Yeah, but we are using that same period as an input to digital controller also.
Yes.
Yeah, but we are sampling at FSW1, let's say 0.90, but we are giving the same pulse, same sampling point.
Yes.
As an input to digital controller.
Yes.
So how to incorporate our computational time that FSW2?
Yes. Yes.
My doubt is like FSW2 and FSW1 are like both are different, or both should be same, or both should be
Okay.
in case yeah,
Yeah,
it
it's
should be
actually a good
different.
question that you have pointed out. So in actual
Okay.
simulation, if you take all these three same, it does not matter because it is a simulation. Whenever you take the sample and whenever you compute the controller, it can compute at a time because it is a simulation
Yes.
software. But in the hardware,
Okay.
it will not happen like that. You have to give some delay, and to mimic the same thing, sir has given here TS delay. So
TS, okay.
after TS delay, it will take the sample. And if you go
Yes.
to the controller, sir has given two terms here, TS plus TC. So TS is the sampling
TC.
delay, TC is the computation
Okay.
delay. So that
Okay.
can be given from here. TC is 0.3T. But even if you give this, or even if you do not give this in simulation, it will work. But in the case of hardware, it
Okay.
will not work. And
It may not. Okay.
yes. So, but that's why we have not considering TC, we are considering TS 0.90. So
Okay.
let me come back here. So let me zoom in this part. Okay. And down. So if I consider this part and if I zoom it, if you see, this is the switching frequency point and it is sampling before this. So this point is the switching frequency and this point is the sampling, right? You are noticing the difference, right? It is happening before switching.
Yes, yes, yeah, yeah.
So this is my FSW at which the switching is happening, and this is my FSW1, and the delay is 0.1T. So SAR has inserted this delay so that it will like to mimic the hardware. So it will get TS time to take the sample and also for computation. So it is taking the sample before, which will be used to generate the controller output at the switching frequency. So this is just to
Hello.
yes.
TS is 0.90, right?
Yes.
So
Let me come back.
0.20 how it?
So this is say switching frequency. So here is the pulse, and here is another pulse,
Okay.
and here is another pulse.
Okay.
So this is
Okay.
FSW, and FSW1 is delayed by 0.90, right? So this is 0.90, and this is 0.90. So like if you talk about the delay, this is FSW1, right? You will say that FSW1 is delayed by 0.90, right? But whatever sample that I'm taking here is being used here, right?
Oh, okay.
But the delay is 0.1T.
Okay, fine.
So that is the overall thing. So this is the
So
output
sampling
voltage.
delay is 0.20, like
0.1T.
that.
Yes. And this is the inductor current. And tuning part we'll discuss in the upcoming sessions, not now. So let me close the waveform. So just to like give an overview, in digital voltage mode control, we have sampling, and that sampled output voltage is subtracted from reference, which is going to the digital controller and is then combined with the RAM, and it is
Hello?
giving a reset function. Yes.
Yeah, one doubt actually.
Yes.
So here, that FSW we keep as T, we keep the switching frequency as FSW sampling time. FSW1. So suppose I am using FSW as fixed, but I am keeping my sampling as twice the time. Like I am
Yes.
taking 2T.
Yes.
Frequency is fixed, but only the multiples I am taking.
Yes.
So can you
What will
simulate that one?
Okay.
Like
So
I'm asking, like what will happen? I'm asking.
okay, so
I
what will
can't
happen is
visualize.
it will update the reference two times in a switching cycle instead of one. So it is not 2T, it is 2 star T. So now I'm making it 2 star T, and I'm also making this 2 star T. I think 2 star T is a mistake. We are sampling it twice, right? So it should be 0.5 star T.
Okay, switching frequency. Okay, fine.
Okay,
Correct.
so
Yeah.
this is 0.5, so 0.5 star T, and here also I'm making 0.5 star T, not 2T. So we are sampling it two times. and let me save it and let me simulate it from here.
But FSW is T only, right?
Yes, FSW is T, that I have not changed, and it should update
Yeah.
2 times in a switching cycle, and let us
2
see.
times in a switching.
And it
So
will,
now
of
will
course,
delay will be point 2 D, right? It will be now. So like it will be square of the delay. Like sampling will be taken before or like.
So let us unlock it and let us see. So if you see, this is the switching frequency, and this is, so from here to here is the switching frequency,
Okay.
and it is updating 2 times. So it is updating here as well as here. It is updating 2 times.
Okay. In the one within that sample, 2 times we are taking
So 2 samples per
in
cycle.
one cycle per cycle.
Yes.
Okay.
If you want to
Sir,
increase,
why
you can
you are
increase.
taking it like you have changed the ramp frequency also?
No. I have not changed RAM frequency. FSW is same. I am only changing the F sampling frequency as well as digital controller computation. So the switching frequency of the converter is same. So the RAM frequency is also same. But I am taking 2 samples per cycle and updating the controller output 2 times faster.
Okay. So one more doubt.
Yeah.
Like last like normally the 0.1T we refer, right? That
Yes.
sample like
Yes.
before the switching we take before like just one. So now if we draw the sample, it will be 0.2T or like 2
Yes,
cycles.
actually,
Like
that again
the
depends upon.
delay will be increased or like my question.
Okay.
Can you
Okay.
draw
So
that?
actually, delay again will depend upon the value that you have taken. See, the delay here, what we have considered, the delay still we have considered TS. So the delay will still be TS. But if you want delay to be changed, then you have to change this value. Say if you want 0.5 TS, then you have to write 0.5 TS.
Okay.
This is a simulation, right? So
Okay.
it will not change. We have to write.
Change. I'm asking. Okay, simulation I understood does not change, but now we change the sampling time, right? 2T. So if we go to hardware, that what you showed that while we are taking the sample just before that one time, so that is 0.20 in the last user.
Yes.
So now we taking 2 times means the delay will be increased to 0.2T. I'm asking.
Okay. So
like that you'll draw
yes.
and show one thing, no? Like that.
So if you consider the computation time of ADC, so this computation time is proportional to the sampling frequency. So depending upon the architecture that is being used in ADC, it will take, say, if you take serial ADC, it will take few cycles. Say it might take, say, 6 cycles, or some might take 2 cycles. Like, so if your switching frequency is decreased, then accordingly this time period will be different. And say like I'm giving you, say it will take 2 times of sampling frequency is this is just an example, is your next TS is 0.2 times of TSAM. So what I'm saying is sampling time into 0.2 times is the that delay. Say if I am taking TSAM to be half, now TS dash will be TS by 2 if TSAM dash is equal to TSAM by 2. This you will get from the data sheet of the ADC. So whatever ADC that you are taking, it will take some time for the computation. That will be given in the data sheet. So for the switching frequency you have considered, you have to check how much is the delay. So that depends upon the ADC that you have selected. When we reach the sensing part and everything, I will show the data sheet and I will show how many cycles it will take.
Fine.
Okay.
Thank you.
So let me quickly, this is the voltage mode control, and next one is the current mode control. So in current mode control, everything is same, right? Only difference is this part. Instead of PID controller, I am using PIA control. Instead of using a ramp, I am using inductor current. So let me quickly go to the lecture 26, which is current mode control. And let me close this. Let me open this, and let me open the current mode control. And so if I go back, everything is same. Only the controller is changed. And in the controller, ADC sampling is exactly same. Error generation is exactly same. This is PI controller. So I don't have the derivative part. I have KID is integral. So KID part I have, KPD part I have, derivative part I don't have because PI controller is sufficient for current mode control, and I am comparing it with the inductor current, which is generating the reset. So everything is exactly same except a few slight changes. One change is PI controller is being used instead of PID, and the other change is we are comparing the inductor current instead of the RAM. So those are the two changes, and the controller gains may be different. So SAR has considered the controller gains accordingly, and this is the voltage. As you can see, there is a huge undershoot, and if you consider the current, and this is the current, so we are going from 1 ampere to 10 amperes, and this is the response. So depending upon the controller tuning, it can be made faster and much if you want oscillations, you can do so. Higher bandwidth and phase margin can be. Is this clear? It will be exactly same like voltage mode control, except these two changes, which are very minor changes. I hope it is clear. If you do not have any questions, then I'll move further. So actually, we are running out of time. So I like to spend more time on the variable frequency. So for the time being, in the valley current mode control, just to be quick. So in the valley current mode control, only change is plus sign and minus sign of the comparator. So here you have minus and plus, here you have plus and minus, and here we have set and reset interchange. So these are the changes compared to mixed and valley current mode control. These are the two changes. So that's why I'm not going into the valley current mode control implementation also, because it is very simple. And this is leading edge modulation with interval one sampling that we have discussed. So I am actually trying to skip fully digital current mode control because we are running out of time. And if you have any doubts, maybe I can discuss this separately because it needs a lot of time. So fully digital, we are emulating the RAM. So there is some other block called triple emulator. So it will take time. I want to concentrate on the variable frequency. If I get time at the end of the session, then I'll come back and I'll explain this. So for the time being, you just rely on SAR's lecture. I'll move on to the variable frequency. Let us solve a few problems. If we have time, I'll come back here. In variable frequency, everything is event based, right? So it is no more uniform sampling. It is event based sampling, and we have minimum off time as well as this is constant on time. So we have monoshot timer with constant on time, and the minimum off time block is also there. So whatever analog we have implemented, the minimum off time logic, it will be exactly same. So it is exactly same as analog. So everything will be exactly same. Only we'll be implementing in the digital, but in simulation it will be same. So when we go into Verilog, we'll discuss how it will vary from analog to digital. So for the time being, it will be same as analog. So this is in which lecture? This is in lecture 28. So let me first close this, and let me open lecture 28 files. Lecture 28. So let me close this. Everywhere it is the same. So SAR has a main file from which the simulink file will be accessed, and then SAR is simulating the simulink file. So here also power stage is set, only we are changing this one. So let me go inside this and let me check what is the difference. So I can see a few differences. So coming to the first part, let me change the color. So this is the first difference. So I am not using uniform sampling. I am using event-based sampling. Why event-based? Because we have discussed in the case of variable frequency, we will use a very event-based sampling. So it is now event triggered, not uniform switching frequency triggered. And so I'll come to this part later. So this is one change that I have observed here. And this is V not of n, and this is same, and V error of n, this is also same. And controller also event driven. So the same trigger that I am using here as well as here, it is just the same. So this is also event based. So now we are no more doing uniform sampling. We are doing event-based sampling. So let me clear and let me go inside the PI controller. This is current mode control. So PI controller. Everything is same, exactly same. Only now things are being triggered by the event. So what is the event here? So this is constant on time, right? Now until this point, everything is same as current mode control, as we have discussed, except event-based sampling, which I will come in a few minutes. And there is something called COT modulator. So what is there in the COT modulator? So these are showing question mark because it has a variable t on constant, which is in the code. So let me run the code. Now the variables will be feeded here. So now you can see the variables are feeded here. So let me explain part by part. Let me use a red color. And so I reference is being compared with the IL, which will give a positive edge, as we have discussed, right? So if this positive edge is coming, that I am using as a trigger. So this is being used for event-based sampling. So this is what event-based sampling. So constant on time is value-based or peak current mode control or value current mode control. Hello. Hello.
Yes.
Yes, so constant on time is value current mode control. So whenever IL is hitting I reference, so this is the event where I am actually sampling the output voltage or operating the controller, everything. So that is the event I am using to sample everything. Now this entire part is same as analog. Entire part is exactly same as analog. If you see, there is one OR block that we have discussed for minimum on time. So I can see two monoshot timer. This is one monoshot timer, and this is the other monoshot timer. So this monoshot timer is for constant on time, and this is for minimum off time. So this and this falling edge, everything I have, whatever I have shown in the analog control, it is exactly the same, no difference. So let me go inside this monoshot timer. So this monoshot timer has one constant block, so T on constant. So whenever it is triggered, so I am triggering at the rising edge. So whenever it sees rising edge, the monoshot timer will be on, and for the specified on time, it will be on. And this is the minimum off time. So I am seeing a falling edge, and whenever it sees falling edge, for off time, minimum off time, it will be turned on. So this is on time, constant on time, and this is minimum off time. So that's how we are implementing the COT modulator. So this is exactly same as analog. So there is nothing new. It will be exactly same. Only the orientation, maybe the block SAR is using another sub module, but here everything is open. So only difference, as I have shown, this is the event. So that event I am using to sample two things. One is this V0. So that event is being used for this V0 sampling, as well as the controller is computing the reference voltage based on this event. So in the case of uniform sampling, we have used uniform switching frequency, but in the case of event-based sampling, I am using event-based. And that event-based is whenever inductor current is hitting the reference. So I have simulated it. So let me see. So this is the inductor current profile, and this is constant on time, right? So it is operating in this way. Depending upon the controller gains, the transient response can be either improved or undershoot can be reduced. So accordingly, it will happen. And now I would like to show you something. If you see, it is event. So exactly at the event, it is happening. Only one sampling is happening in a cycle. And if you come back here, see the sampling is happening here and the sampling is happening here. So the time period of this and the time period of this is not same. So the time period is varying variable frequency, but the sampling is happening once per cycle because there is a single event in a switching cycle. So we are using that event to take the sample or do the controller computation. So only one sampling is happening. But when you go into steady state, now the switching frequency is more or less fixed. So it is like fixed frequency because it has attained some steady state where the frequency will be constant. So and the sample is being taken at the bottom. So the bottom value is regulated at 1 voltage. So this is all about constant on time. And there is what difference is between constant on time as well as constant off time. There are very few differences. One is this comparator. So here we have plus, here we have minus. So here we have minus, here we have plus. And this is valley current mode control. And this is peak current mode control. And here we'll have inverter because it is constant off. We have to invert the monoshot timer. Here there is no such inverter. And here we have minimum off time. Here we'll have minimum on time. Minimum on time. So this is peak based. So what are the changes? So here also the event is same. Whenever inductor is hitting the peak, this is the event. Here what is the event? Whenever it is hitting the valley, this is the event. And here this is the event. So I am using this event to take the sample, and here I am using this event to take the sample. So there are no additional changes in the MATLAB. So let me just open. So we'll also be confident about this. So this is in lecture 29, I guess. So in lecture 29, I am not simulating because it will be somewhat similar, or maybe I can simulate and show as well. So let me just open this. Sorry, the Simulink file. Let me open. Okay, and let me simulate. So everything is exactly same. Only the controller block is different. So let me go into the controller block. Now it has event-based sampling. So this is T of trigger, T of trigger. I think it is simulating, right? Okay, I have actually simulated the wrong file. So let me simulate the main file. So this T of trigger we are using now to take the event-based sampling and as well as PI controller. So everything is exactly same. Now let me go into the constant off time. Constant off time is also everything is same, right? The event is this event. The event, same event I'm using to do the F trigger. So F trigger is what? F trigger is the T of trigger. So whenever this inductor is hitting the reference that I'm using to take the sample. And now this is what? This is constant off time. In the case of constant on time, this is constant on time. Now in this case, this is constant off time. I cannot open it because the simulation is running. We have to wait until the simulation over. So this is constant off time, and this is minimum on time, right? And the entire logic will be exactly same as what we have used in the constant on time. So there are two changes. One is the event at which we are sampling will change, and the inductor will be comparator will be in opposite sign, and there will be a NOT gate at the output. So that is all the major difference between this and that. And the event interval one sampling, event based sampling, we have already discussed. So now that the simulation has come, let me show the inductor current profile. So this is what? Constant. Constant off time. So off time is constant and on time is variable. So off time is constant. So this is the simulation, and let me close this as well. Let me open this. So monostable, it has T of constant time, and the minimum on time is T on minimum. So only these minor changes are there. Apart from that, everything is exactly same. So this is variable frequency, constant on time, constant off time as well. So in mixed signal hysteresis, what do we have? We have two comparators. Here one comparator, here another comparator. And I reference, either you do peak or you do valley or you do average. So depending upon that, your this thing will vary. I reference minimum and I reference maximum will vary. So if you do peak, this is I reference. This is I reference minus delta I. If you do valley, this is I reference. This is I reference plus delta I. If you do average, this is I reference plus delta L by 2. This is I reference minus delta L. So this is explained in lecture 30. So this will be our last simulation. So let me just quickly show our last simulation. So this is the main file where which we have to simulate, and this is the Simulink file. So let me close this Simulink file, and this is now open. So what is different? Everything is same. It is also event-based sampling. So there is an event using which we are sampling this PI controller. This is also exactly same. only this hysteresis logic will change. So in hysteresis logic, what we are using, say this is I reference we are using, and I reference minus delta IH we are using. So what is this? I reference and I reference minus delta IL, which is a peak hysteresis control, right? So I am using peak hysteresis current mode control. And what is the event I'm using? Whenever I reference hits the peak IL, that is the event that I'm using to sample. And one is generating reset and the other one is generating set. So this is the hysteresis control. So let me just quickly simulate it and check. You are understanding, right, everyone? Hello.
Yeah, yes, yes, yes.
Hello.
Yes, yes.
Yeah. So let me just quickly simulate it. So this is one and this is hysteresis. So hysteresis on time is variable and off time is also variable. So depending upon the gains that we have chosen, the ripple will be in that limit. So what is the ripple here? 19.5 to 21.5, I think around 2 amperes limit. If you want to change the limit, then you can change the limit here. And say delta is 2.5, so accordingly you can change. Again, there is less than a minute, so you come back quickly. After that, we'll solve problems. So this is all about mixed signal, current mode control, fixed frequency, variable frequency. Now let us move to the problem solving session. So this meeting will end. I'll create a new meeting where we'll be discussing about few problems. So it will strengthen your concepts. Before we move on, do you have any questions? So we have already crossed 2.5 hours, but it's okay. I'll just quickly go through all the questions. So it will be very useful for your assignment solving or exam, final exam as well. So let me just quickly go through. I hope my screen is visible, right? Let me close this. And is my screen visible?
Yes, it is visible.
Yeah. So I'm really happy that you people are staying till the end. Okay, thanks for staying. So this will give me motivation to help you even more. So we'll solve few problems. So in this MATLAB based week, the problems will be also based on MATLAB. So there are two things. One is the digital controller and the other one is the MATLAB simulation. So first, let us start with the digital controller. So the question is as follows. I'll quickly go through. I may not solve the question here, but you please try to solve because we are already running out of time. So I have given a digital PID controller whose transfer function is given as this. So you are asked to find KP, KD. So can anyone tell me what is the idea behind how to solve this?
KP plus Ki by S plus KD into S.
Write
Where
the digital transfer function and
1
compare
minus
it.
Z inverse.
Yes, KP plus 1 by S means 1 by Z inverse, and KD into S means 1 minus Z inverse. So if you solve this, like if you multiply by Z minus Z and take common, you will get this. So now I have to compare these two, right? I should compare this one with this one. So if you compare, can you please tell me what values I'll get? So first term is KP plus KI plus KD is 15.1 and 2KD plus KP is 20. You have to note this minus sign. So minus sign is also here. And KD is 5. So from this final equation, I will get KD to be 5. If I substitute KD here, I will get KP to be 10. If I substitute these two here, I will get KI to be 0.1. So now this will give KP, KI, KD in digital domain. So you have to note this. Why I'm saying or stressing digital domain? Because these are digital values. So one thing you have to take a note. If I consider analog, say analog, V error of T is nothing but KP into, sorry, V control voltage of T is, or maybe I can discuss in the next slide. So next slide, I have asked in the analog domain. So I have asked KP, KD in analog domain. I have given sampling time. So the relation between, so the left hand side are the digital parameters and right hand side are the analog parameters. So why this relation? So coming back to that, say I have V control voltage of T in analog domain. I have KP into V error of T plus KI into integral v error of t dt plus kd into d v error of t dt. Right. So, but if I consider in the digital v con of n, what I am considering kp into v error of n plus ki into say ui v error present minus v error previous. So it is like integration from say this is like I am integrating from v error of n from n minus 1t to nt, and in derivative I will write what v error of n minus v error of n minus 1 by time period t. Right. So this is the actual digital controller implementation. So this is nothing but ki into v error of nt minus v error of n minus 1t into the time period t. So you take a note of these things. So let me go back. And I'm going back to the digital controller. So if you consider my digital controller expressions, so in my digital controller, I am not considering that time period t, the t term here, right? So that t term is already embedded in this ki. So whatever kp, ki, kd we are considering, that already has the terms. So if I go back to the equation where I'm generating these things, so my kpd is kp. My kid, I am not considering t in my equation, right? So ki into t is my new ki. So this ki into t. And similarly, kd by t is my k derivative. So kdd is my kd by t. So these are the digital gains that I am considering. So this t also I am considering in these expressions. So these are the digital parameters, and these are the analog parameters. So this is the relation between digital and analog. So if you are in your assignments, if you are asked this, then you have to solve it accordingly. So in the previous equation, what we got kd to be 5, right? We got kd is equals to 5 and kp is equals to 10 and ki is to be 0.1. So
Sir, could you please repeat once? Please go back to the previous slide. Problem number A.
okay.
Sir, here there are decimals in the, like, may we use the same decimals in digital, or we have to like floor or seal those values?
Sorry. Can you please repeat? Your voice is not clear.
Hello?
Yeah. Can you please repeat? Your voice is not audible.
Is it audible now?
Yes, yeah.
Sir, if KPI got 15.1, then may I use the same 15.1, or may I have to like truncate it like 15, or may I use 16 then?
No. Actually, in this question, the intention is they have given this controller and they are asking you to find the KPK KD. And we know the direct relation, right? So you just have to directly compare to get this KPK KD, whatever values that we are getting, that is this. But in the case of implementation, if you would like to consider this to be 16z square or 15.1z square, that is up to you. If I consider this 16z square, then what will be my KP? It will be 1, right? Instead of 0.1, it will be 1. So then you have to check the simulation, whether it is faster or slower, whether you are okay with that transient response or not. And then you have to implement. So in this question, it is not that like, can you use 16 or not? So we have given the PID controller and we are asking you what are the KP, KD terms. So I'm directly comparing it with this equation and I'm getting KP, KD terms. Understood.
Okay, sir.
Okay. So in the next question,
Sir.
I am asking the analog equivalent. So the analog equivalent are dependent like this. So if my KP is 10, my KPD will also be 10. And if my KI is 1, my KID will be 0.1 into 1 microsecond. So whatever the value, that will be my KID, and my KDD, sorry, this KID is 0.1, which is equals
Sir?
to KI into T. Sorry.
Sir, this KP, KI, KD that we got from the last problem is also digital.
Yes, yes. So
Digital.
this is the continuation of problem 1. So this is the B part. So for the previous question, find the gains KP, KI, KD in analog domain. And the sampling time is given,
Sir?
and the digital and analog are related like this.
Sir, but the left side is KPD is analog, right?
No, KPD, D for digital, KPD is digital, and KID is analog. So KID I got in the last question, which is 0.1. So I want to find the integral Ki. So Ki is 0.1 into 10 to the power 6, because T is 1 microsecond. So Ki in analog is 10 to the power 5. And if you go into KDD, which is nothing but KD by time period T, and KD I got 5. So KD is what? 5 into 10 to the power minus 6. You understood?
Sir, you mean both are the digital, you mean?
Like
that
I
is
mean
the
to say,
KP, KI, KD we got.
whatever we got in the previous question, these are KPD, KID, and KDD. So they are in the digital domain. And for these gains,
Okay.
I am asking what are their analog equivalents. So if you see in source code as well, so KP, KI are what? In analog. In digital, what is SAR doing? KPD is KPD, KID is KI into T. So that is what I am doing. KID is KI into T. So for digital controller, you have to convert the gains into digital equivalent, and for analog, you have to convert this into analog equivalent. But the derivation is coming from this, and you have to keep this in mind, the relation. I hope this is clear.
Really, in the last problem also we are getting digital only, but now again we are converting into digital KPD, KID, K. These three things come from the last problem.
No. I am not converting into KPD. I am calculating KP, KI, KD.
In
this
this
question,
problem.
I am calculating KP, KI, KD. And in this question, these are KPD. These are KPD, KID, and KDD. So they are in digital domain. I am asking you to find KPD, KID, KID. And using this KPD, KID, KID, I am asking you to find KP, KI, KD.
Okay, so the last problem we find that 5, 10, and 0.1 are KPD, KID, and KDD.
So these are KDD, KPD, and KID. Okay, so now if we go into the next question, so can you tell me which architecture this is? Okay, we'll go slow by slow. So is this analog or mixed signal or fully digital?
Mixed signal.
Mixed signal.
Mixed
Yes.
signal.
So this is mixed signal. Is this fixed frequency or variable frequency? How do I know from the sampling? So is this uniform sampling or even based sampling?
Uniform.
So uniform sampling, so it is fixed frequency. And is this current mode or voltage mode?
Current.
Current mode. It is not
Current mode.
And is this peak or valley? How do I know? I can know from set. If set is coming from FSW, is it peak or valley?
It is trailing edge.
Valley.
So, no, trailing edge is not valley, right? Trailing edge is peak, right? In the peak, it is trailing. Understood? Valley means the inductor current is leading, right? So this is valley, and this is peak. So
from trailing edge, how can we say that if it is peak or valley?
So trailing edge means the inductor current is trailing the reference. So it is below the reference, and leading edge means inductor current is leading. So inductor current is above the reference. So this is I reference, and this is inductor current. So inductor current is leading I reference. So inductor current is above. So it is valley. And in trailing edge, inductor current is below reference. So this is peak current mode control or trailing edge. So that's why I'm saying it is peak current mode control and not valley. Understood?
Because sir, it is setting, right? Because
and this is one way, and another way is the whatever switching frequency that you are taking, if it sets, then it is peak. If it resets, then it is valley. So you can tell it from both the ways. So whatever way is comfortable
sir,
to you, you can.
So setting means once it reaches the value point only it will set, right?
No. Like see, if you consider the peak current mode control,
Okay.
Like is this set point or reset point?
This is the reset point.
Reset point, right? So reset point is coming when we are comparing IL to I reference. So reset point is coming when we are comparing IL to I reference. And set point, this is set point, right? Set point is the switching frequency.
Okay. Okay.
So okay. And so is this uniform sampling or event-based sampling?
Uniform
Yeah,
sampling.
So this is uniform sampling. And is this trailing edge or leading edge?
Trailing edge.
Peak, so trailing edge.
Trailing edge. And so that's why this is mixed signal peak current mode control with uniform sampling. So this is one problem. So your problems will be based on these kind of things only. So either you will be asked to find which architecture is the correct architecture, or you will be asked which architecture is this. So you have to be this much confident and clear about the concepts. So actually this is fully digital. As I have not discussed fully digital, I will not be discussing this now, but you please go through the fully digital SARS video lecture, and then you can come back and solve it here. This will be uploaded in my Google Drive. So I'm not going in detail. So this is fully digital. Keep this in mind. So this is something called ripple emulator. As I have not discussed, I am not discussing now. Let us go to the next problem. So this is which architecture?
When this ripple emulator concept will be discussed, sir?
If you want me to discuss, I will discuss maybe before next week. I can discuss sometime, or I ask you to go through SARS video lecture, or I will see if I can make a separate YouTube video and upload in my channel. I will also do that, but I might not get time, so I'll discuss in the next week. But I recommend you to go
So the
through
output
SARS
of
video
ripple
lectures.
emulator is also clock. So the output of ripple emulator is also a step ramp, right?
So this is a ramp signal. So I is it will be like this.
Okay.
So
the output of ripple emulator?
Output of so this is the inductor ripple emulator. So this entire block is the ripple emulator. So it needs inductor current as input. It will take the sample and it will give me IE means I emulated. So it will give me I emulated. Let us not discuss the details because I have not taught you or discussed the working of this. So
no, sir. I just want to know how the wave shape of this IE.
How the
wave shape of this IE.
Wave shape of this IE. So the slope of this IE is decided by something called MC, slope of this emulator. So whatever value you give MC, depending upon the slope. If you give higher slope, then it will go like this and like this. If you go smaller slope, then it will go like this. So this MC decides the slope. So I have asked this. So MC is the slope for the ripple emulator. And this block is ripple emulator. And where is it used? It is used in the fully digital peak current mode control. So is this voltage control or current control? This is current control. It is not mixed signal. It is fully digital. So you should be having a better understanding of this block. Sir has discussed like in a very detailed manner. So you can go through Sir's lecture as well. For the time being, let me skip this part and let me go to this architecture. So is this analog or mixed signal or fully digital? Mixed signal. And fixed frequency or variable frequency?
Variable.
Variable.
Variable frequency.
And constant on or constant off or hysteresis?
Constant
off. So from this I can say it is constant off. Also from this you can say it is constant off, and minimum on time, so constant off. So it is constant off, and it is a current mode control as we know. And is this peak or valley or average?
Peak.
Peak. Not valley, not average. And with sampling.
Sir, how can we say that it is peak
or valley? That is a good question. I can decide from the sign. So whenever IL is positive, then the reset pulse is coming. So whenever IL is crossing I reference, it is giving me the pulse. So I can say IL is trailing and I reference is leading. So that gives me that this is peak current mode control, or we can say that constant off is always peak, and constant on is always valley. From that also you can say, and this is event-based sampling because it is fixed frequency. And from this, if it is peak, it is trailing edge, not leading edge. So from this I can get that. So this is mixed signal constant of trailing edge peak current mode control with event-based sampling. Now coming to this architecture, do you remember which block is this?
Hysteresis.
No. I can see two monoshot
Constant.
timers.
Constant.
So it can be either constant on or constant off. So how do I know the difference? One difference is you can get from this. So here I reference is less than or equal to IL, or IL is greater than or equals to I reference. So IL is plus, I reference is minus. So which is what? IL is plus, I reference is minus.
Here I reference is greater than IL.
No, this is less than or equal to. This is less than or equal to symbol. So I reference is less than or equal to IL. So I reference is greater than or equal to IF. So this is constant off. This is one way of telling. The other way of telling is I know there is an inverter at the output and I can see an inverter here. So which means this is constant off. So if it is constant off and if it has two monoshot timers, then I know that this is constant off monoshot timer, and this is minimum constant on monoshot timer. So this block is constant off modulator with minimum constant on time. And now you know this is a variable frequency current mode control. So I know that this is constant off from this inverter or this ILI reference notation. And is this peak or valley? I have discussed constant off is what? Peak or valley?
Peak.
Peak. So constant off is peak. And then with sampling, we know it is event-based sampling. And trailing edge or leading edge, it is peak, so trailing edge. Now I have one important question. What is the constant off time? So this is constant off time. So constant off time is 1.83 microsecond. So constant off is how much? 1.83 microsecond. And what is the minimum on time? So this is the minimum on time. So it is into 10 by 10 if I do, it will be 29.
0.2 nanosecond.
20 nano. 20 nano, right? 20 into 10 to the power minus 9 is 2 into 10 to the power minus 7.
Sir, how you are getting the minimum on time here?
So this is the monoshot timer for minimum on time, right? And it says 2 into 10 to the power minus 8 seconds. So which is what? 20 into 10 to the power minus 9 seconds. So my minimum on time is 29. So the overall thing is mixed signal constant off time, trailing edge, peak current mode control, event-based sampling. Now, one final question. This is which architecture? I have two comparators. Hysteresis. So this is again mixed signal, not analog, not fully digital. And this is variable frequency. This is now hysteresis control. And is this peak or valley or average? How do I say? I say from the I reference. So how this is one is I reference. One is I reference minus delta IH. So is this peak or valley or average?
Valley.
No, this is peak. Let me go back to. So if you see I reference and I reference minus delta IH, so it is peak. So you have to be very careful. Or you can remember one thing. If I reference is used as peak, it is peak. If I reference is used as valley, it is valley. If it is used for none of them, then it is average. So you can remember in that way. So depending upon how you want to remember, that is up to you. So and let me go back to again the question, problem 7. So this is peak because I reference is used as peak, so it is peak. And what is delta IH here? This is the delta IH. So delta IH is the ripple of the inductor current that we are trying to maintain. And with sampling, since it is variable frequency, event-based sampling. So it is mixed signal, peak, hysteresis, current mode control with event-based sampling. So these are the type of questions that you can expect in the assignments or exam. So you have to be this much clear. So see, for every architecture, I can ask plenty of questions. You can ask these questions to yourself, and you can solve for this for every architecture. And I'll check with the professor whether you can get the MATLAB models or not, and I'll get back to you. Also, I'll ask the TS to solve your queries regularly. Sorry for the inconvenience. And they'll try to answer your questions by tomorrow night I'll discuss with them. I'll also discuss with the professor. So I'll take a note that I have not discussed the fully digital control. So in the next class, I'll discuss within 10 to 15 minutes this what is the implementation, MATLAB, everything. So in today's session, we have discussed the analog MATLAB simulation, and then we have discussed about digital controller, and then we have discussed about the digital MATLAB simulation. So I hope I have cleared all your questions, and thanks for staying till
question.
then. Yeah,
Sir, whether how to decide whether which we can convert to digital and which we have to stay in analog?
So so let me go to voltage mode control. Everything is digital. It is fully digital because everything ramp, everything is in digital. Now coming to current mode control, it has two things. One is mixed signal, and another one is fully digital. So in mixed signal, V0 is analog, and V0 is digital, and I0 is analog. In fully digital, IL, V0 both are in digital. So depending upon the architecture, you will know whether it is in digital or not. But you may ask me, should I go to mixed signal or should I go to fully digital? Mixed signal is easier compared to fully digital, and it has its advantage because fully digital, we are sampling both IL and V0 and we are emulating, which will pose so many, what should I say, stability issues compared to mixed signal. So you may ask me, sir, so fully digital, why are we going for fully digital? Why not mixed signal? This also has advantages because we are sensing IL. We can use plenty architectures inside the algorithm, and I can implement complex algorithm in Verilog code, and I can use IL. But performance, it might not be as much good as mixed signal, but still there is something called event-based sampling in fully digital, which I have worked on and I have published paper. So using this, I can achieve better transient response, almost close to mixed signal. So research is going on both fully digital as well as mixed signal. So each of it has its own advantage. So depending upon your requirement, which architecture you have, and depending upon your components, you can either go to current mode control, voltage mode control, or current mode mixed signal, fully digital. But when you have decided the architecture, you should know which is in digital and which is in analog. So here nothing is in analog, everything is fully digital. So I hope this has clarified your query.
Yes, sir. Sir, one more thing.
Yes.
Like if current mode control is not available in single loop, it is available in two loops only?
Yes, current mode control. If I say current mode control has IL, V0. So this is a two loop control. When I say current mode control, it is two loop control because both IL and V0 are there. When I have only V0, this is single loop control. So current mode control, it is always two loop control, and voltage mode control, it is always single loop control. But whether you want this to be in analog,
can't I use only one loop for current loop control?
No. Because current mode control needs both V0 and IL, right? So V0 has to be regulated. So you have to do V reference minus V0 to regulate V0. And I am either using peak current mode control or valley current mode control to control both profiles. So in current mode control, I have flexibility to control V0 as well as I0 independently. So as you have to control this, as you have controlled this, so this needs one loop, this needs another loop. So it is a two loop control, and it cannot be used in a single loop. Single loop you can use when this I reference is there, right? So I reference is coming from outer loop, right? So if I give constant I reference and I directly compare it with the inductor current, so there is no controller here. So this is giving reset pulse, and this is giving set pulse. So now what I'm doing, I'm fixing the peak inductor current. But who is regulating the V0? No one is regulating the V0. For this peak current, whatever be the V0, the converter will be giving me that V0. So this is outer loop I am opening. I am only giving constant I reference. So there is no V0 loop. In this case, V0 is not regulated. So If you want V0 to be regulated, you have to use two loops. But if you want to
Sir,
give
what
constant
will
I
happen
reference,
if I-
then you can give constant I reference as well.
Sir, what will happen if I use only single loop control then?
So if you want to use single control loop, you have to give constant I reference. So I reference is constant. IL will be accordingly. So
Yes, sir.
V0
That is
is
for two loop
adjusted
control, it
accordingly.
is clear.
V0 is adjusted accordingly. So you have no control on V0. If your V0 to be 1 volt, it may or may not be 1 volt. So V0 is adjusted accordingly and you don't have any control over it.
Yes, sir, that is clear. If I use only single loop control for VMC, then won't the current will be controlled?
No. In single loop control, we are regulating V0, but we don't have any control over inductor current profile. Say I don't want inductor current to cross 10 amperes. I cannot do this in voltage mode control because I don't have control, right? I am not bothering about inductor current. Whatever maybe the PID controller gains that I am selecting, that will generate the control voltage that will affect the duty ratio. So I am not controlling IL. If you want to control both, you need to loop control. You cannot do with a single loop control.
Okay. Sir, one more thing I want to know is like how the PID controller is giving the reference voltage when we feed it with an error voltage.
So as I have discussed, say this is the PID controller GC of S in analog domain. This is V error of S. So we have this equation, right? Kp plus Ki by S plus KDS. So this into V error of S, this gives me V control of S. So accordingly, it will be decided. But now you will be asking how it is happening. So when I teach the Verilog code of voltage mode control, I will go step by step, line by line, how the control voltage is calculated. So for the time being, you assume that if I give error voltage to controller, it will give me control voltage. But how it is happening step by step, I'll explain in detail when we do Verilog. So I think it will be in lecture 71 to 73 voltage mode control is there. So I'll explain line to line code there. So then you will get a full better understanding. For the time being, just remember this. Okay, if you don't have any questions, I'll end the meeting here.
Yeah, good
Thank
night,
you,
sir.
sir.
Thank you.
Thanks for attending. See you in the next week. Bye. Good night.
Bye.